Hi there, you're in the lab with your mate JJ. Today is Old Book Teardown Day. We're going to be tearing down an old book. My silly job title for today is Sparky. I'm Sparky. The book I have for you today is quite old. It was published in 1948. Look at this old thing. It's got a kind of a cloth hard cover. You can barely read the writing. It's a monster. It's really big. It looks yellowed and maybe a bit moldy. It's really old book, but it looks like it'll be fun. It's from Westinghouse, which is a company that makes electronics goods. So anyway, we'll learn more about this old book. It's 77 years old. It's older than my dad. So this is a really old electronics book. As I said, published 1948. So what we're going to be doing in this video is just looking through it. We're just going to flip through and see what's in it, cover to cover, and then we'll be done. So let's pop over to the bench and see what's in this old book. All right. So look at this old thing. You can barely read the title. In fact, we'll turn the page to find the title because it's in here. There's some sort of a note up there, but I can't read it. I don't know what it says. Something about old books, isn't it? This is Industrial Electronics Reference Book. There you go. And it's by the electronics engineers of the Westinghouse Electric Corporation, published by John Wiley and Sons, Incorporated, New York, Chapman and Hall Limited, London. Fascinating. 1948 it's dated. Can you see that? Let's see if I can get you up there. Yeah, you can see mostly. All right. Well, I'm definitely going to be reading the introductory material. So let's read the preface and see what they had to say for themselves. When was that dated? April 1948. So this is a note from April 1948. Since 1940, widespread expansion has taken place in the field of electronic engineering. Marked advancement was made in the industrial phase of electronics, with the result that this branch of engineering was directly related to the momentous production record of industry during this period. Developments took place so rapidly that it was almost impossible for one not highly skilled in such equipment to keep pace. The need for a digest embracing the application as well as the design data for industrial electronic equipment under one cover was evident. The Industrial Electronics Reference Book was written to satisfy this need. This book has been prepared with the hope that the technical data and application information set forth will enable those concerned with the application and utilization of electronic apparatus to have a better understanding of the possibilities and limitations of such equipment. The book, therefore, has been aimed at the practicing engineer who is faced with the problem of understanding the underlying principles as well as the scope and limiting factors of electronic apparatus as it is applied to industrial processes. It is felt that the book will also be of material value to graduates of engineering schools who are entering industry for the first time and who will be faced with the problem of approving or rejecting electronic equipment for use in industrial functions. The Industrial Electronics Reference Book has been written by a group of engineers, each thoroughly versed in his particular branch of the subject. These particular authors were chosen because of their broad experience, deep interest, and close association over a period of years with that phase of the industrial electronics field about which they have written. The authors have been intimately associated with the rapidly expanding electronics field during the past decade and have imparted many valuable and lasting contributions to this branch of electrical engineering. Chapters 1 through 3 cover the fundamental and theoretical concepts of basic laws governing the production and control of electronics. The kinetic theory of gases is reviewed. Modern views of atomic structure are discussed, and the electronic theory of solids is examined. The theory of electron emission is covered, and the types of emission that emitting surfaces and the types of emission and emitting surfaces are discussed. Theories covering the different types of emission, such as field emission, secondary emission, thermionic emission, are set forth. The many factors entering into the control of free electrons are pointed out. These cover space charge, electron motion in magnetic and electric fields, and forces on electrons in magnetic fields. Chapters 4 through 10 embrace the design, operation, and construction features of the different types of electronic tubes, which are the fundamental part of any piece of electronic equipment. The design and operation of vacuum tubes, gas tubes, X-ray tubes, cathode ray tubes, as well as photoelectric devices and ultraviolet radiators are discussed. Electronic circuit components, such as the different resistance forms, capacitance and inductance, and also tuned circuits, filters, and transformers, are covered in chapters 11 through 14, and the different circuits for rectifiers, amplifiers, oscillators, and various control circuits are presented in chapters 15 through 18. The design and application factors relating to transmission lines and antennas, subjects which are becoming increasingly important in the industrial electronics field, are covered in chapters 19 and 20. The many different types of industrial equipment are reviewed in chapters 21 through 34. Power rectifiers and inverters, radio frequency heating equipment, power line carrier equipment, electronic instruments such as electrometers, high frequency ammeters, time interval and speed meters, stroboscopes, balancing machines, electron microscopes, and many others are explained. Industrial X-ray, motor control, precipitation equipment, regulation devices, resistance welding, and photoelectric equipment are discussed. Factors influencing design, application, and operation are emphasized. Limitations as well as advantages are set forth and discussed. Chapters 35 and 36 have been included to give the reader an indication of the factors involved in the care and maintenance of electronic tubes and electronic apparatus. A list of references appears at the end of most chapters so that the reader may easily find additional information on any one of the specific subjects involved. The book committee and the authors wish to acknowledge the work of G.P. Cardwell, D.R. Lynch, J.T. Carlton, W. Reed, and C.J. Madsen, who so ably assisted in the task of coordinating and following the book material through the production stage. The Westinghouse Industrial Electronics Book Committee. Book Coordinator, B.E. Rector, Electronics Engineer. Okay. And then it looks like they're all book coordinators except for the last guy who's the chairman. So we've got Bergwin, Advisory Engineer, Electronic Control Engineering, Aaron Harmon, Manager of Engineering, Industrial Electronics Division, Hutchison, Director, Research Laboratories, Jeff Jones, Electronics Engineer, D.D. Nowles, Manager of Electronics Engineering Lamp Division, E.H. Vedder, Manager of Engineering Electronic Control Division, and the Chairman, F.R. Benedict, Manager, Industry Engineering Department, April 1948. Cool. I'm gonna have a break, get coffee, and then we'll settle in, see what's in this book. All right, I got my coffee and I got my bottle of water, and I'm ready to go through this book. Let's start by looking through the table of contents. I think there was 36 chapters. There were indeed, and then an index. The index begins on page 671. So, a few hundred pages in the book, 600 or 700. All right. Physical background of industrial electronics, electron emission, control of free electrons, electrical conduction in gases, vacuum tubes, gas tubes, photoelectric devices, industrial X-ray tubes, cathode ray tubes, ultraviolet radiators, circuit elements, tuned circuits and filters, transformers, vacuum tubes as circuit elements, rectifier circuits, amplifier circuits, circuits for oscillators, circuits for industrial control, transmission lines, antennas, general requirements of rectifier applications, mercury arc rectifiers for power application, inverters, radio frequency heating, power line carrier, electronic instruments, industrial X-ray applications, electrostatic precipitation, electronic motor control, regulation, resistance welding control, industrial photoelectric control, applications of ultraviolet radiations, radar fundamentals and applications, care and maintenance of tubes, care and maintenance of electronic apparatus. There you go. Those care and maintenance chapters 35 and 36 written by the same person, C.J. Madsen. All right, and then we're off. Chapter 1, Physical Background of Industrial Electronics. What is electronics? Electronics is that branch of physics or electrical engineering which deals with the phenomena of the flow of electric currents through vacuum, gases, and vapors. And wires. This chapter opens the subject with a review of the physical background of electronics, the processes by which electricity passes from one body to another through high vacuum or through gases are more numerous than the ways in which electricity passes through a wire, and these processes are more intimately bound up with the fundamental nature of matter. In fact, the study of the processes which are put to work in this branch of electrical engineering has been one of the chief tools of the physicist in learning what we know today about electrons, protons, atomic structure, and related topics. Kinetic theory of gases. According to modern physics, a gas is made up of a large number of molecules which occupy only a small fraction of the total space taken up by the gas. These molecules are independent units which move about with very little influence on each other except when they collide, like billiard balls on a billiard table. For many purposes, it is not necessary to specify the internal structure of the molecules themselves. When the gas is at a particular temperature and density, its molecules move at random. At any instant, some are moving fast, others slowly and in different directions, and the particular behavior of any one changes rapidly as it collides with other molecules or with the walls of the containing vessel. The most outstanding mechanical property is that the gas exerts a pressure on the walls of the container, and this is interpreted to be due to the large number of molecular impacts against the wall. The average pressure on the wall is equal to 2/3 of the total kinetic energy of the translatory motion of the molecules contained in unit volume. For gases at low enough pressures and at high enough temperatures, far enough from the regime of the liquid state, the pressure is proportional to the density of the gas and to the absolute temperature, and inversely proportional to the molecular weight. This is expressed as P equals P RT on M, where T is the absolute temperature, P, or is it rho, I'm not sure, is the density, P is the pressure, M is the molecular weight, and R is a universal constant. In both engineering and physics, in this field it is customary to use CGS units. That practice is followed here with convenient reference to other unit systems. If T, I have heard of CGS units, I forget exactly what it means. Is it centimeter, gram, second, maybe? I suppose I should look it up, I'll go and check. Yep, CGS is centimeter gram second, which I guess is some sort of metric-based system. Very good. All right. In both engineering and physics in this field, it is customary to use CGS units. That practice is followed here with convenient reference to other unit systems. If T is the temperature on the Fahrenheit scale, then capital T, the absolute temperature in centigrade degrees, is T equals 5/9 of T plus 256. Oh, that's interesting. Nice binary number in there. Density usually is given in grams per cubic centimeter. All right. Anyway, then we're off talking about gases and such. Some charts there. The atomic nature of electricity. In the older experiments on electrostatics and electric currents, there is no indication that electric charge is anything but a continuous fluid, just as one does not recognize the molecular structure of water from the study of hydraulics. The existence of electrons and their properties, although interesting, therefore hardly plays a role in the classical field of electrical engineering. This is entirely different in electronics, which is founded on the detailed consideration of the elementary atomic units of charge. The ways in which elementary substances combine to form chemical compounds can be explained by saying that matter consists of atoms of definite elements. Similarly, the first evidence that electric charge always occurs in definite units came with the discovery that, in electroplating, a definite amount of electric charge is needed to plate a gram mole of a univalent metal. This amount of charge is called the Faraday, and it is equal to 96,500 coulombs. This is interpreted by saying that the univalent metal ions in solution, as for example each silver ion in silver nitrate solution, bear a definite electric charge such that the total charge carried by a gram mole of them, that is 6.0228 times 10 to the power of 23 of them, is equal to 96,500 coulombs. Therefore, the charge on each of them is E equals 96,500 divided by 6.0228 times 10 to the 23, 1.6 times 10 to the minus 19 coulombs. It is generally believed that all electric charge occurs in amounts that are multiples of this basic unit, which is called the electronic charge. Studies first made in the 1890s by J.J. Thomson. Oh, look, it's another J.J. J.J. Thomson on deflection of cathode ray beams by electric and magnetic fields in tubes that were primitive forerunners of the modern cathode ray tube, indicate that such beams behaved like a stream of charged particles moving according to known mechanical laws. From these experiments, the ratio of the charge to the mass of each particle could be determined. The modern accepted value for this quantity is E divided by m equals 1.76 times 10 to the 8 coulombs per gram. This is a large value compared with the same quantity for the lightest atom, hydrogen, for which E on m equals 10 to the 5 coulombs per gram. It's 3 orders of magnitude less. These results are interpreted by supposing the cathode ray particles to have the same charge as the hydrogen ions involved in electrolysis, but to have a mass that is 1,837th of the mass of the hydrogen. These little negatively charged bits of matter are called electrons. According to modern views, all matter is made up of atoms, which are themselves constructed of electrons, and positively charged central nuclei that are relatively massive. Because of their small mass compared with the natural units of positive charge, electrons generally move much more rapidly in electric fields, and so usually electric currents are predominantly due to motions of these negative charges, although this is by no means always the case. Positive ions in gas discharges have been studied, but never have shown particles of large E on M like that of electrons. And the values are always comparable to the values of E on M appearing in electrolytic ions. On the basis of this kind of evidence, we conclude that negative electric charge comes in small units called electrons, whose mass is about 1 on 837, that of hydrogen, the lightest atom known. Positive electric charge is always associated with masses of the same magnitudes as those of the atoms of matter, the magnitudes of the charge being the same as of the electron. This statement overlooks the existence of the positron, a particle with positive charge and mass the same as the electron, which is observed only in experiments involving potentials of millions of volts or in nuclear transformation or cosmic ray studies, and which thus far has played no role in industrial electronics. And then we're off for the structure of atoms. The modern views of atomic structure are built on the ideas of Rutherford and Bohr, which were stated about 1912. According to their views, each atom consists of a central positively charged nucleus, which contains most of the mass of the atom, surrounded by enough electrons to make the atom electrically neutral. The atoms of the different chemical elements are distributed principally by the number of such electrons and correspondingly by the magnitude of the positive charge on the nucleus. The massive central nucleus is itself a composite structure made up of two kinds of particles. These are protons, which are simply the positively charged nuclei of ordinary hydrogen atoms, and neutrons. Neutrons are particles having almost the same mass as protons, but having no electric charge. The nature of the forces which hold these particles together within the nucleus is not fully known, and it forms one of the important problems of nuclear physics, which is the investigation of the properties of the atomic nucleus. Although changes in the nucleus can be produced artificially by special high voltage bombardment with positive ions, and although they occur spontaneously in naturally radioactive materials, they have played no role up to now in industrial electronics and will not be discussed here. It will be noted, in passing, that one can produce artificially radioactive materials which are destined to play a great role in industrial chemistry and in medicine in the future. The number of electrons in the atom is called its atomic number, and each chemical element is distinguished by a particular atomic number. These are given in Table 1.1, in which the known elements are arranged in a periodic table. The goal of atomic theory, which is well on its way to having been achieved, is to correlate all physical and chemical properties in terms of the detailed working out of this picture of atomic structure. There we go. So we've got a great big honkin' periodic table. Looks a bit different here to how we're accustomed to seeing it these days. And there's a whole lot of heavier elements that they haven't found yet. This one goes up to 96. Yeah, interesting. So there was a lot more to happen after 1948. This is reprinted with permission from Fundamental Chemistry, 2nd edition by G.H. Deming, published by John Wiley in 1947. The atom is by no means a simple system in which the electrons move around the nucleus according to Newtonian laws of motion, obeying the usual forces between electric charges. On the contrary, it has been learned during the past 30 years that the behavior of electrons in atoms and molecules is governed by a different set of physical laws, having some surprising characteristics to one who is versed in the mechanics of ordinary bodies. The mechanical principles applicable to it in atomic theory are known as quantum mechanics. This forms an extensive part of modern physics. One of the most extraordinary things about a beam of electrons is that it behaves in some ways as if it were a wave motion instead of a stream of particles. In fact, there is no proof that a beam of electrons is one or the other, for it has some of the attributes of a stream of particles and some of those of a wave motion. This peculiar duplex character is one of the most puzzling things in modern physics, and the nature of a cathode ray beam is not completely understood, in spite of the fact that enough is known to cover all practical cases likely to arise. To be more explicit, a cathode ray beam behaves like a stream of particles in the way it is deflected by electric or magnetic fields. In fact, it was by such calculations that E on M was measured experimentally. But it behaves like a wave motion when it is scattered by going through a thin plate of crystalline material. Figure 1.3 shows the pattern produced by allowing electrons from an originally sharp beam to fall on a photographic plate after it has traversed a thin film of cobaltous oxide. The sharp rings in the picture show that the electrons are scattered in definitely determined directions. This phenomena is known as electron diffraction. Electron diffraction can be interpreted by assuming that if the electrons, regarded as moving particles with velocity v centimeters per second, are scattered by a crystal lattice, they are scattered as if they were a wave motion of wavelength lambda equals h on mv, where h is Planck's constant, which is 10 to the minus 27, and m is the mass of the electron in grams, in a more practical and convenient form, blah, 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 blah. All right, we're off to atomic energy levels. Ionization functions. This is ionization functions for common atoms. Number of ions formed per centimeter path per millimeter pressure at 25 degrees Celsius. Helium. Okay. Helium, hydrogen, nitrogen, hydrogen chloride, HG. I don't really know what those things are. I'm not much of a chemist. Electronic theory of solids. Quantum mechanical theory has also greatly extended our fundamental knowledge of the behavior of electrons in solid materials. The mathematical difficulties are very great, so this part of the subject is less developed than the theory for isolated atoms. Electrically, the most important distinction among solids is that between good conductors, which are metals, and good insulators, which are non-metals. It is desirable to break the classification down further to include a class known as semiconductors. These are materials like zinc oxide or cuprous oxide, whose conductivity is much poorer than ordinary metals, but much better than inductors. In contrast with metals, the conductivity increases in increasing temperature. This conductivity of semiconductors is believed to be due in all cases to the effect of impurities or slight departures of the composition from that of the chemical formula. The conductivity values are extremely sensitive to the purity and to the means of preparation of the material. The non-conductors may be further classified into types as A, glasses or supercooled liquids which do not have a well-defined crystal structure, B, ionic crystals like sodium chloride or magnesium oxide distinguished by electrolytic conductivity at high temperatures, C, valence crystals like diamond and quartz, distinguished by great hardness, irregular cleavage, and very low conductivity, and D, molecular crystals such as the rare gases hydrogen or methane, as the rare gases and hydrogen or methane, because hydrogen and methane aren't rare gases, when cooled below the melting point. The electrons in a metal are of two kinds, bound and free. The bound electrons are those which make up the inner shells of the atoms and exist in essentially the same states as when the atom is in the gaseous state. It is transitions between states of these tightly bound electrons that are involved in the emission and absorption of X-rays by matter. The fact that the X-ray spectra are very little changed by chemical combination or changes from gaseous to solid state shows that the inner electrons are not affected by such changes. A little diagram here of a cubic lattice. Very good. All right, and then that's the end of this chapter. Chapter 2, Electron Emission, J.W. McNall. Because of its important duty, the electron source, usually referred to as the cathode, can be considered the heart of every electronic tube. The phenomenon of taking electrons from the external circuit and making them available as free electrons to whatever vacuum, gas, or vapor-filled region is desired is defined as electron emission. In order to use electronic tubes intelligently, it is essential to be familiar with the characteristics of the various electron emitters and the theories of electron emitting processes, because they determine many of the tube limitations and capabilities. Theory of electron emission. There are four general classifications of electron emitters. 1. Thermionic, 2. Field, 3. Photoelectric, and 4. Secondary emitters. Although these four types of electron emitters are radically different in their physical and operational characteristics, their mechanisms of emission are similar from the standpoint of electron theory of metals and semiconductors. As shown in Chapter 1, potential energy distribution in a metal can be represented by Figure 1.8. Okay, that was earlier. At a temperature of absolute zero, the maximum potential energy of an electron is Wi, the distribution of electrons having energies below Wi being as shown in Figure 110. All right, blah, blah, blah. Then we got the contact difference of potential. Potential energy diagram for two metal surfaces nearly in contact. All right. We've got thermionic emission. A big table here. This table, table 2.1, the experimental value of the work function and the thermionic emission constant for several metals. All right, lithium, beryllium, carbon, sodium, magnesium. And then on we go. Velocity distribution of thermionically emitted electrons. Characteristics of thermionic cathodes. Types of thermionic emitters, including pure metals, composite surfaces, emission in the presence of a field, the Schottky effect. Electron emission from a surface depends upon the height of the potential barrier, and reduction of that height results in increased emission. The larger thermionic emission from surfaces of low work function is an example of this effect. For a given surface, the height of the potential barrier can be decreased by applying sufficiently strong electrostatic fields to the surface of the emitter. By reducing the height of the potential barrier, the effective work function is reduced by the same amount, since the Wi level is unaffected by the application of external fields. To evaluate the decrease in effective work function requires a knowledge of the various forces which give rise to the potential barrier. The first retarding force on an electron attempting to escape is a Coulomb force and is caused by the atoms in the crystal lattice. This type of force was discussed in section 1.7 and was illustrated in figure 1.8. This resulting force decreases rapidly as the electron leaves the surface of the metal and is relatively weak when the electron is several atomic distances away. When the electron succeeds in getting several atomic distances away from the metal surface, the metal appears to the electron as a relatively homogeneous smooth surface rather than as an irregular surface of non-uniform charge caused by the discrete atoms of the crystal lattice. A second retarding force, commonly called the image force, is believed to act on an electron removed from the metal surface by a distance large compared with the atomic spacing of the crystal lattice. The image force can be considered as that between a charge, -E, and a plane conducting surface at distance x away. Such a force is identical with that between two charges, -E and +E, separated by a distance of 2x, as shown in figure 2.7t. Field emission. Characteristics of photoelectric emission. Theories of photoelectric emission. Secondary electron emission. Theory of secondary electron emission. Electron emission resulting from bombardment of the surface by electrons is called secondary electron emission. In measuring secondary electron currents, all electrons from the secondary emitter are unavoidably collected. If a material is bombarded by electrons, the electron current from it consists not only of emitted electrons, but also of primary or bombarding electrons reflected from the surface. The distinction between reflected and true secondary electrons can be made on the basis of their energies. Secondary electrons are only those electrons actually emitted from the bombarded target. The distinction is important theoretically, but is of limited practical significance because usually the number of electrons actually emitted from the target is much greater than the number reflected. The secondary emitting properties of a surface usually are described in terms of its yield. Is that delta? I'm not sure what that is. Which is the average number of secondary electrons produced by one bombarding electron. Let me have a look at the... So what are we looking at here? What was that number? Yeah, it's delta, lowercase delta. Theory of secondary electron emission, yield and types of surfaces, metals, oxides, compounds, composite cathodes, insulators, thin film field emitters. Characteristics of secondary electron emission. That's the end of the chapter. That's a long list of references. Control of free electrons. H.J. Daly and J.H. Finlay. After release from a solid body or emitting surface, an electron can be controlled and can be made to perform various functions. Since such an electron has a known electrostatic charge, the path it will follow can be accurately predicted when the difference of electric intensity can be calculated or measured. This chapter deals with electrons in motions, the prediction of their behavior, and the electrostatic means for controlling them after their release from the cathode. Okay, so this is the control of free electrons. Potential gradient, electrostatic potential, and electric intensity. Space charge. I wonder what that means. If a space between parallel plates contains no space charge, the voltage gradient between those plates is constant. If the negative plate is an unlimited source of electrons, and if a potential difference exists between the plates, the number of free electrons between the plates will increase until their number is limited by the potential difference between those plates. The voltage gradient is now no longer constant. When electrons pass from the cathode to the anode, then the graphical representation shown in figure 3.1 changes to that shown in 3.2. As the electron density between plates 1 and 2 increases, E and the potential distribution change as the electron density increases from 0 to the maximum that potential E can produce. The potential distribution then changes from that shown by the dotted line to that of the heavy line, and the current is said to be space charge limited. Figure 3.2 shows that E varies over the distance from x equals 0 to x equals a. When x is approximately 0, then dVdx is also approximately 0. This indicates that for full space charge, the electric intensity or voltage gradient at the source of electrons is essentially 0. Poisson and Laplace's equations. Constant potential line distribution. Space charge current in parallel plane diodes. Space charge current in cylindrical diodes. Of course, diodes were tubes, weren't they, back in the day? They weren't semiconductors back then. Potential distribution in space charge free diodes. Cylindrical and parallel plane triodes. Electron motion. Thus far, electron motion has simply been called a current in a vacuum. This section deals more with the intrinsic properties of electrons when they are influenced by various electrostatic forces. Electron motion in an electrostatic field is so analogous to the motion of a projectile that the term electron ballistics is often used. Oh yeah. Force on an electron in a magnetic field. All right. Motion of an electron in a magnetic field. Motion of an electron in parallel electric and magnetic fields. Motion of an electron in perpendicular electric and magnetic fields. Motion of an electron in electric and magnetic fields making an arbitrary angle with each other. Motion of electrons in a radial electric field and an axial magnetic field. Cutoff characteristics of a cylindrical magnetron. Applications. The equations derived in the foregoing section apply as well to the motion of positive and negative ions as to the motion of electrons. In using the equations for ions, different values for mass must be used. The charge on ions is either positive or negative, and the magnitude of the charge is equal to the electronic charge or an integral multiple of it. Therefore, the equations can be applied to the motion of electrons or ions by cathode ray tubes, mass spectrometers, cyclotrons, magnetrons, and other devices. Hardly any references compared to the previous chapter. Chapter 4, Electrical Conduction in Gases by D.E. Marshall. If a quantity of gas is included in a tube with a cathode which can emit sufficient electrons, the tube has the following characteristics. 1. Anode-cathode voltage becomes almost independent of anode current, and in magnitude it is about equal to the ionization potential of the gas. 2. Grids are unable to modify anode-cathode current after conduction starts. Control consists of blocking conduction before starting. 3. The electrostatic field at the cathode is in the proper direction to assist in electron emission. In a phototube, introduction of gas causes amplification of photoelectric currents, otherwise the current would be derived from cathode emission alone. In a gas-filled tube with 2 or more electrodes having no independent electron emission, applied voltages of several hundred can cause discharges. These phenomena form the basis for gas tube engineering. Although the theories evolved to account for these effects are not in general completely satisfactory, they aid in understanding the phenomena. All right, ionization, space conduction through ionized space, space charge phenomena, volt-ampere characteristic of electrodes in a plasma, electron emission as generated or increased by positive ion fields, phenomena at the anode, arc back. Voltage rating is one of the least understood factors in tube design. Since losses in gas tubes are a function of the current, the power rating is limited by circuit voltage. It might seem feasible to design gas tube circuits for high voltages, thereby increasing the power range of the tubes, but technical considerations limit circuit voltages. Technically, the voltage rating is limited because of the tendency of the tube to arc back. This arc back is a mysterious phenomenon. It is a spontaneous reversal of conduction in a tube. An arc spot appears on the anode, electrons are emitted from it, and reverse conduction follows. These are some of the causes of arc back in pool and hot cathode tubes. 1. Flakes of emission coating on the anode. 2. Flakes of insulation coating on the anode. 3. Improperly shielded junctions of dissimilar materials in the anode structure. 4. Impurities in the anode material. 5. Overheating of the tube. 6. Too rapid application of reverse voltage after conduction. 7. Poor design causing localized fields. 8. Mercury on anodes. 9. High velocity material from the cathode arc spot striking the anode. Wow, what a hassle. Deionization. Amplification of small electron currents in gases. Self-maintaining discharge, breakdown. Glow discharge, cold cathode discharge. Control of gas discharge by electrostatic fields. Control of gas discharge by ignition. Oh, wow. The theory of operation of an igniter closely parallels the theory of the mercury pool cathode discussed in section 4.6. Some computations indicate that the passage of current down the igniter, as shown in figure 4.10, concentrating at the mercury edge, can result in fields of about 10 to the power of 6 volts per centimeter over atomic dimensions at the igniter mercury junction. This is comparable with the fields at the electrode originating from positive ion space charge. It seems reasonable that the same phenomenon that maintains the arc with fields of 10 to the 6 volts per centimeter in the one case would operate also in the second. Therefore, it can be assumed that the igniter operates because of field emission near the mercury igniter junction. Control of gas discharge by magnetic fields. Permatron. A tube can be made similar to the thyrotron, except that its control is magnetic rather than electrostatic. In general, this tube has an anode and cathode similar to the usual thyrotron elements, and an electron collector similar in appearance to the grid of a thyrotron. As many parts as possible are non-magnetic. A magnetic field transverse to the direction of the electron's flow from cathode to anode controls conduction. Such a combination of electrostatic and magnetic fields causes the electrons to move in cycloidal paths. If the magnetic field is great enough, the electrons never advance far enough in the direction of the anode-cathode field to gain sufficient energy to ionize the gas. They finally strike the collector, which is connected to the cathode. If the magnetic field is weaker than the the electrons advance further and are able to ionize the gas, and conduction starts. As in a thyrotron, anode current must fall to zero before control can be regained. Chapter 5, Vacuum Tubes by H.J. Daly, J.H. Finlay, and E.C. Ockress. Vacuum tube construction, thermionic emitters, pure tungsten emitters, thoriated tungsten emitters, oxide-coated cathodes, anodes, control screen and suppressor grids. Cross-section of air cooler for tubes showing sections mentioned in the text. Envelopes, exhaust procedures, bases. Vacuum rectifier tubes, like diodes. The vacuum rectifier tube, termed kenetron to differentiate from the gas-filled rectifier termed phanotron, basically consists of a source of electrons and a collector of electrons. Electrons move from the cathode to the anode only if free electrons are available at the cathode and if the anode is positive with respect to the cathode. Triodes. Feel like we missed diodes. Tetrodes, pentodes, and beam power tubes. Multi-purpose tubes. Tube design parameters. Class A, Class B, Class C. Wonder if that's the same as they have with amplifiers. I don't know. Yeah, I think they're talking about amplifiers again. Plate modulated Class C amplifier service. Grid dissipation, maximum anode voltage, maximum negative grid voltage, maximum radio frequency grid voltage, maximum radio frequency grid current, minimum water flow. Minimum water flow rates are established on the basis of calculations and measurements which indirectly establish the velocity of water along the surface of the anode to prevent formation of steam bubbles. The quantity of water specified usually is a compromise between maximum water pressure available or desirable and the water velocity. Adequate cooling can be obtained at higher water velocities and lower volume, but only at the expense of higher pressure. Minimum airflow, frequency for maximum input, conventional tube design as related to performance at high frequencies. I wonder what they think a high frequency is. Give me some megahertz. If tubes have active elements of 1/16th wavelength. The klystron and its resonant cavity. General design of klystron. Velocity modulation. Conditions for maximum power conversion. I wonder if they're talking about impedance matching. Velocity modulation is useless by itself, for no output has been obtained. To get an output signal, the velocity modulated beam must be converted into an intensity modulated beam. One way of doing this is by means of the drift space. Alright. Mathematical treatment of bunching. Phase shift in the klystron. The klystron as an amplifier and frequency multiplier. The klystron as an oscillator. Reflex klystron. Secondary emission reflex klystron. The magnetron oscillator. Static characteristics of the magnetron. Dynamic characteristics of the symmetric magnetron. Equivalent circuit representation of the symmetric magnetron. Operational diagrams for magnetrons. Scaling of magnetrons. Some basic relations of symmetric magnetrons. And then a long list of references. 2 pages, that's quite a lot. Chapter 6. Gas tubes, D.E. Marshall. By definition, a vacuum tube containing sufficient gas to influence its operation is a gas tube. The influence of gas in general results from its ionization, so that positive charges are available to neutralize the electron space charge. Gas tubes, therefore, can conduct large currents at comparatively low voltage drop and therefore operate at high efficiency. The term gas tube covers tubes containing gases that can condense within their operating temperature range, as well as tubes with gases which cannot so condense. Among the former are mercury vapor tubes, the latter are xenon, neon, and argon-filled tubes. Gas tubes range in size and capacity from large multi-anode pool rectifiers to small control thyrotrons or even smaller protective spark gaps of various types. Large tubes are applied in power rectification and inversion, in heavy current resistance welding control. Smaller ones are used as rectifiers for DC supply in radio receivers, as control relays, lock-in relays, and for other similar applications. Detailed descriptions and ratings of commercial tubes are available in technical information sheets published by tube manufacturers. Alright, then we're off. Gas tube operation, control in DC circuits, control in AC circuits, phase control in AC power conversion circuits, phase control in AC welding circuits, gas tube technical data, characteristics, ratings, use of technical information, general gas tube ratings, maximum peak current, maximum average current, maximum surge current, peak inverse and forward voltage, thermal ratings, arc drop voltage, ratings and characteristics of hot cathode tubes, heater on filament voltage, heater or filament voltage, heater or filament current, cathode heating time, ratings and characteristics of thyrotrons, shield grid characteristics, cross-section of WL672 shield grid thyrotron. Diagram of thyrotron grid current characteristic before conduction. Grid ratings. Grid capacitance characteristics. Ionization and deionization time. Characteristics and ratings of multi-anode pool-type tubes. Look at that, the thing's a monster. Multi-anode mercury arc rectifiers. Wow. Characteristics of excitrons. Ratings and characteristics of ignitron rectifier. Ignitron. So that stuff earlier wasn't ignition, it's ignitron. I got that horribly wrong, didn't I? Alright. Low voltage ignitron rectifiers. High voltage ignitron rectifiers. Okay. Rectifier igniters. I really don't understand this technology at all. Ratings and characteristics of resistance welder control ignitrons. Ignitron welding ratings. Welding control igniters. Igniters used in welding control ignitrons are developed chiefly for their characteristics in intermittent duty. Their ability to start the tube when it is cold is of primary importance. Usually, igniters in welding control circuits are operated by so-called anode firing, as shown in Figure 626. Igniters are connected to the anode through a thyrotron. When the ignitron begins to conduct, ignitron voltage falls and becomes too low to cause current through the thyrotron in series with the igniter. Current and voltage for operating the igniter are drawn from the load. Therefore, operation of the igniter depends upon the size of the load controlled by the ignitrons. As shown in Figure 627, the current to such a load usually lags the voltage by an angle dependent upon load power factor. When the control thyrotron operates, supply voltage is applied to the igniter through the inductance of the load. Igniter voltage and current are zero initially and will rise to a rate determined by load inductance until current through the igniter rises to the firing value. Igniter firing time, measured from the time at which the thyrotron begins to conduct, varies with the circuit constants as well as with the igniter characteristics. Below the firing point, current causes the igniter to heat and in general tends to increase firing current. If the impedance of the load is low, the source voltage is impressed on the igniter through the series current limiting resistor. In such a circuit, as shown in Figure 626, current and voltage rise abruptly and continue until the igniter fires. In this example, the igniter firing time is clearly defined. In the rating sheet, igniter voltage, maximum positive peak required, and the similar current characteristic indicate the values required. Applied constantly, they cause the igniter to fire in a less than ignition time maximum. Characteristics of cold cathode tubes. Chapter 7. Photoelectric devices. Photoelectric effect may be defined as an electrical charge which is produced by the absorption of radiation by matter. This is a rather broad definition, and to make it less inclusive, it is customary to include only electrical changes in which electrons are freed from the atoms so that they constitute an electric current. The definition should be further modified to exclude radiant energy with wavelength longer than infrared. Alright, take a break. Credit for the discovery of the photoelectric effect, upon which the modern phototube is based, goes to Heinrich Hertz. Oh, there we go. He made this discovery in 1887 while he was engaged in experimental verification of Maxwell's electromagnetic theory of light. Hertz discovered that the length of a spark induced by an auxiliary micrometer gap was reduced if the light from the primary spark was prevented from falling on the gap. He traced this effect to ultraviolet generated in the discharge of the main gap, which fell on the electrodes of the second gap. The effect was increased if a large, clean plate was used as the negative electrode. Hertz did not continue his investigation, but Wilhelm Hollwachs took up the problem. He believed the effect was not dependent upon oscillatory spark discharges. Hollwachs' investigation showed that a clean zinc sphere connected to a gold leaf electroscope and negatively charged to a gold leaf electroscope and negatively charged would lose the charge if illuminated by light from an electric arc. He found further that light had no effect on a positively charged sphere, but that if the positively charged body was placed in the neighborhood of a negatively charged body which was irradiated by light, the positive body would lose its charge. Hollwachs concluded from these experiments that if a body is irradiated by ultraviolet radiation, negative electricity leaves the body and follows the electrostatic lines of force. In 1899, this negative electricity was identified by Leonard and Thomson, I wonder if that's our mate J.J. Thomson from earlier, as electrons. The effect discovered by Hollwachs is often known as the Hollwachs effect. Several other investigators continued the study of the photoelectric effect. The most comprehensive work was accomplished by Elster and Geitel, who first showed that certain alkali metals, particularly sodium and potassium, when amalgamated by mercury, become photoelectrically sensitive to visible light as well as to ultraviolet radiation. Because active surfaces such as sodium and potassium cannot be kept clean in air, they enclosed the sensitive surface in an evacuated glass bulb. This was the forerunner of the modern phototube. To Elster and Geitel must also go the credit for conceiving the first gas phototube. The same observers studied the effect of polarized light on a photo surface. Okay, fundamental laws. The first law, second law, third law, fourth law, fifth law, and then we're done. That's a lot of laws. Radiant energy, the black body. Radiant energy spectrum. And they break out the ultraviolet section, ultraviolet portion of spectrum, visible portion of spectrum. Oh, there you go. Yeah, that's cool. Sources of radiant energy. Measurement of radiant energy. Classification of photosensitive devices. General design considerations of phototubes. Cathode. Let's go back to the classification. This is classification of photosensitive devices. We've got the non-directional type. We've got the conventional type. We've got the low leakage type. We've got the N type, and we've got the cartridge type. There you go. General design considerations of phototubes: cathode form, interelectrode capacitance, microphonics, leakage, glass envelope, preparation of photosensitive surfaces, composite surfaces, pure metal surfaces, a little bit of, I don't know what that is, a bit of dirt. All right. Types of phototube surfaces, ultraviolet photosensitive surfaces, photosensitive surface designations. S1, S2, S3 surfaces, S4 surface, gas phototubes, vacuum versus gas phototubes. Stability, linearity, dynamic response, glow voltage, sensitivity. Secondary phototube characteristics: dark current, thermionic emission from the cathode, glow currents, leakage current, interelectrode capacitance, fatigue, temperature, maximum current. Multiplier phototube, photo glow tube, iconoscope, orthicon, image iconoscope, image dissector tube, photoconductive cells, photovoltaic cells. Definition of photometric quantities: light, luminous flux, lumen, luminous intensity, candle, candle power, illumination, foot candle, luminous efficiency, radiant energy, spectral radiant energy, radiant flux, radiant energy density, radiant flux density, radiant intensity, spectral radiant intensity, total emissivity, spectral emissivity, flux calculation, and then references. Chapter 8, Industrial X-ray Tubes by Joseph Lempert. The discovery and use of X-rays by Roentgen in 1895 may be regarded as the first practical application of electronics. The importance of this discovery in introducing electronics is secondary only to the role X-rays played in starting the complacent 19th century world with a phenomenon which could not be explained in terms of classical physics. X-rays have served as a key to modern quantum physics and all the phenomena associated with the modern concept of the atom. In addition, X-rays as used in radiology and X-ray diffraction are extremely valuable industrially. Finally, X-rays have filled a vital human need in medical radiology and therapy. One of the reasons why X-rays were not discovered sooner is that special methods such as light-sensitive emulsions and ionization chambers are required for their detection. In addition, with the exception of natural radioactive processes, the combination of materials and circumstances necessary to produce X-rays do not occur in nature. Since X-rays result from the collisions of high-speed electrons with atoms, a source of such electrons is necessary. High voltages are generally used for accelerating electrons. There's a note here. Although high-speed electrons can be produced by magnetic fields and other methods, acceleration by high voltage is at present the simplest and most economical method of achieving 1,000,000 electron volts or less. 1,000,000 electrovolts. High voltages are generally used for accelerating electrons. The process of X-ray production is confined to the evacuated chamber of an X-ray tube to avoid an excessive number of collisions between the electrons and the atoms of the gaseous medium, thus preventing arc over between electrodes and maintaining electrical insulation. In addition, vacuum prevents oxidation of tube parts which operate at high temperature. Physical properties of X-rays. The continuous X-ray spectrum, characteristics X-ray lines, absorption and scattering of X-rays, factors affecting quality of X-ray examination, contrast in radiography, scattering in radiography, unsharpness in radiography. Unsharpness. Let's read about unsharpness. What can they tell us about that? The finite size of focal spots in X-ray tubes produces radiographic images which are not completely sharp. The width of the unsharp region is a direct function of geometrical factors and may be defined from the similar triangle relations in figure 810a according to the following equation. Okay. The term unsharpness is commonly used in place of the less negative expression sharpness because it can be defined and measured. Gas-filled X-ray tubes, standard types of X-ray tubes, tubes with maximum ratings between 70 and 95 kilovolts, tubes with maximum ratings between 100 and 125 kilovolts, then up to 200 and 250 kilovolts. The Betatron, a magnetic induction electron accelerator. Factors affecting the design of X-ray tube envelopes. Some photos in there. Design of anode and cathode assemblies. Manufacture of X-ray tubes. Rating of X-ray tubes. Limitations on short-time loading of X-ray tubes. Heat capacity, limitations in exposure time and length and frequency of successive exposures. Cooling curve of an X-ray tube. Continuous rating of an X-ray tube. Ratings of X-ray tubes in tube heads. Then we're up to references. That's the end of the chapter. Chapter 9. I'm going to have to readjust this book. Hang on a sec. How are we doing? Can you see that? Mostly. I'll put that there. How's that? It's fairly good. I can move that a bit. Cathode ray tubes. PE Vols and PE Grandmont. A device using a beam of electrons, cathode rays, as a writing element is generally classified as a cathode ray tube. The usual abbreviation, CR tube, is used throughout this chapter. There are two types of CR tubes, the sealed-off tube and the demountable tube, which have completely different applications. Components of a CR tube and its auxiliary equipment may be divided into three functional classifications. 1. Devices that produce, control, and focus a beam of electrons. These devices are generally called the electron gun. It is necessarily inside the evacuated envelope of the tube. 2. Devices that cause deflection of the electron beam. Either electrostatic or magnetostatic fields may be used, and the deflecting fields may be produced by devices inside or outside the evacuated envelope of the tube. Usually the beam can be deflected in two directions at right angles to each other. 3. The device, called a screen, that indicates the position and intensity of the beam. Some of the beam energy can be translated into visible light due to incandescence, fluorescence, or phosphorescence. The beam can produce a latent image on photographic film. In any case, the beam must strike the screen material, so the screen is inside the evacuated envelope of the tube. Electron source, electron motion, electron path in electrostatic field, electron path in magnetic field, simple electrostatic lens, simple magnetic lens, immersion lens, bipotential lens, gas focusing, electron gun, beam deflection, defocusing or deflecting systems, screens, transit time, applications, oscilloscopes and oscillographs. Since the electron beam can be readily deflected electrically, and since it leaves a trace that persists a short time, it is well adapted to visual reproduction of the variations of electrical quantities, and since it is easy to convert other forms of energy to variations of an electrical current or field, the possible applications are numerous. There we go. They've got television. The CR tube is important in television systems where it provides the means of reproducing the transmitted image. The transmitted signal and the receiver circuits cause the CR beam to scan the screen from left to right. The beam starts at the upper left and, after reaching the bottom, returns to the upper left to scan between the lines previously traced. This interlacing reduces flicker on the screen. The transmitted image is reproduced by intensity modulation of the CR beam. During the retrace, when the beam travels from right to left, its intensity is cut to zero by a blanking signal on the grid. For television surface, while screens are preferred to the screen Willemite screens generally used in an oscilloscope. Special CR tubes have been developed with red, blue and green screens for an experimental all-electronic colour television system. Yes, well, we have colour television now. Ultraviolet radiators. Production of ultraviolet radiation. Sorry, this is Chapter 10, Ultraviolet Radiators by H.C. Rentschler. Production of ultraviolet radiation. Low pressure ultraviolet lamps. The ultraviolet transmission of the glass. Length and diameter of lamp tube. Electrodes. Gas and gas pressure. Lamp temperature. High pressure ultraviolet lamps. Measurement of ultraviolet radiation. It is important to have a simple method of measuring the effective intensity and the amount of radiation used in a specific application. Since different wavelengths are not equally effective, a meter that evaluates the different wavelengths of radiation in proportion to their effectiveness is desirable. The photoelectric threshold of a metal has a definite wavelength which is readily reproduced. A specific use of ultraviolet radiation determines the longest wavelength that is effective. By proper choice of a phototube, it is possible to measure only radiation shorter than the threshold wavelength of the phototube, and therefore only that radiation which is effective for the application. Thus, the phototube responds only to the ultraviolet which produces the reaction under investigation. As an example, the bactericidal action of ultraviolet is confined to radiation shorter than 3000 angstrom units. The photoelectric threshold of tantalum is approximately 3000 angstrom units. A tantalum phototube therefore measures only the bactericidal radiations regardless of the source. The bactericidal action for radiators below 3000 angstrom units increases with decreasing wavelength, reaches a peak at 2660 angstrom units, and again diminishes for shorter wavelengths. Chapter 11, Circuit Elements by D.G. Little. The three basic circuit elements are resistance, capacitance, and inductance. These elements never exist separately. Every electrical circuit always contains all three circuit elements. Each circuit element has unique properties. Capacitance has the ability to store energy in the form of an electrostatic field in its dielectric material. And inductance stores energy in the form of a magnetic field surrounding it. Resistance cannot store energy, but it always converts the electrical energy into some other form of energy, usually heat, light, or other electromagnetic radiations. Linear resistance. Nonlinear resistance. All right, linear resistance. The resistance of a current path may be considered as inversely proportional to the number of free electrons in that path. Metals such as silver or copper apparently have large quantities of free electrons. Consequently, when an electromotive force is applied, the flow of electrons is large and the resistance is said to be low. Insulators such as silk or porcelain have few free electrons and hence have a higher resistance. A perfect vacuum with no free electrons has an infinite resistance. An electric current may be thought of as a migration or flow of free electrons through and between the atoms and molecules of the conductor. In practical terms, the current of 1 amp at a point in a circuit means that 6.28 times 10 to the 18 electrons flow past that point each second. In all temperatures except absolute zero, the atoms of the conductor are agitated thermally and they retard or resist the flow of free electrons. This resistance generally varies directly with absolute temperature. Thus, at normal temperatures, metallic conductors have specific resistances depending upon the material, but at absolute zero, the resistance of all conductors approaches zero. Metallic conductors have constant resistance at constant temperature, or the voltage drop is directly proportional to the current. Such resistances are known as linear resistances because the value of the resistance is not affected by the current through it or the voltage across it, so long as temperature remains constant. The unit of resistance is the ohm. The international ohm is that resistance offered by an unvarying electric current by a column of mercury at the temperature of melting ice, 14.4521 grams in mass, of a constant cross-sectional area, and of a length of 106.300 centimeters. A current of 1 ampere flowing through a resistance of 1 ohm causes a potential difference across the resistance of 1 ohm. I would have put that the other way. Don't they say a volt is what pushes an amp through an ohm? Here they say the current flowing through 1 ohm causes the potential difference across the resistance of 1 volt. It's got its causality back to front there, doesn't it? I think it does. I don't know. Does a current cause a volt or does a volt cause a current? Nonlinear resistance. Currents in other media, semi-metallic materials, high vacua, and ionized gases do not follow the linear law. In high vacua, the current varies as the 3/2 power of the voltage. In ionized gas, the voltage drop is determined by the ionization potential of the gas, which depends upon the pressure and temperature and concentration of the gas, and this voltage drop is relatively independent of the current. Other kinds of conductors are known generally as varistors. There's a note here. Oh, the varistor is a trademark of Bell Labs. There you go. Bell Telephone Laboratories. All right. Other resistance forms. Inductance. Looking at some inductors here. Very good. Capacitance. Okay. Variable air capacitor. Yeah. Combinations of resistance and inductance. Combinations of resistance and capacitance. Combinations of inductance, capacitance, and resistance in AC circuits. Distributed constant in AC circuits. Inductance, capacitance, and resistance may only be considered to be lumped constants as an approximation. It is sometimes necessary, owing to the circuit conditions or the operating condition, to take into consideration that these quantities actually are distributed over the circuit. An example of such a circuit is the transmission line. Characteristics of a circuit having distributed L, C, and R may be quite different from those of a similar circuit having lumped constants. Any circuit element always contains some inductance, some capacitance, and some resistance, regardless of its nominal function. Thus, a resistance has some inductance and capacitance, an inductance has some capacitance and resistance, and a capacitance has some resistance and inductance. Under certain conditions, usually at higher frequencies, these secondary or residual components cannot be neglected, and they may actually predominate in determining the characteristics of the component. Frequently, these constants are distributed. For example, the distributed capacity between turns and windings of a reactor. An interesting example of distributed constants is the single-layer coil shown in figure 1122. Such a coil is often used to feed direct current to a plate or grid circuit of a vacuum tube oscillator or amplifier. It presents high impedance to high-frequency voltages. On direct current and at low frequencies, this coil acts as an inductance, but the capacitance between its turns combines with the inductance to change the resistance and impedance of the coil as the frequency is varied, as illustrated in figure 1123. Where is 1123? Down here it is. Oh, look at that. It's a funny looking... Look at that. All over the place. Circuit elements of inductance, capacitance, and resistance in DC circuits. Okay. Series circuits. Typical keying circuit. Tuned circuits and filters by Ruben Lee. In general, tuned circuits and filters are used to obtain maximum current, voltage, or power from a system at desirable frequencies, or to reject them at undesirable frequencies. Incidental problems of regulation and transient response are important, but they arise because of circuit elements, the primary function of which is frequency discrimination. Hence, tuned circuits and filters are characterized by quantitative and usually comparative relations at different frequencies or in different parts of a circuit. A series resonant circuit. Parallel resonant circuit. Coupled circuits. Oh, they're using transformers. Power amplifier output circuits. Harmonic content. Modulation. Tank circuit frequency ranges. Principles of wave filters. Filter design charts. Constant K filters. M-derived filter. Limitations of wave filters. Several factors modify the performance of the wave filters shown in figures 1227 and 1228, especially in the cutoff region. One of these is reflection caused by mismatch of the characteristic impedance. The load resistor usually is of constant value, whereas the image impedance usually drops at 0 at cutoff. The resulting reflections cause a rounding of the attenuation curve in the cutoff region as shown on curve V of figure 1232. This is more pronounced in constant K filters than in M-derived filters because the impedance match is better in the M-derived type. Artificial lines. Sometimes a certain amount of time delay may be interposed between one circuit and another, or if a transmission if a transmission frequency, up here it goes, if a transmission line is not an exact multiple of 90 degrees long, some means must be found to increase its length to the next higher multiple of 90 degrees. For either of these purposes, artificial lines are used. They may operate either at a single frequency or over a range of frequencies. Okay. DC power supply filters, single phase full wave rectifier, polyphase rectifiers, multi-stage filters, DC power supply regulation, tuned power supply filters, filter currents, filter transients. References. Chapter 13, Transformers by Ruben Lee. In weight, not transistors, they haven't been invented yet. In weight, transformers used for electronic circuits range from a few ounces to many tons. Ratings vary from 0 to several million watts, and the frequency range extends from less than 1 cycle per second to several megacycles per second. As might be expected, many different designs are used for these transformers, but one principle common to all is Faraday's law. E equals negative n to phi to t, which means that the voltage induced in any coil of n turns is proportional to the number of turns and to the rate of change of magnetic flux in the coil. For a given voltage, if the rate of change of flux is small, the number of turns must be great. Consequently, low-frequency transformers have many turns and high-frequency transformers have few turns. As core materials are improved, it becomes possible to operate transformers with higher and higher flux densities in the cores, and therefore fewer turns become necessary. Thus, the upper limit of frequency is extended. All right, construction and size, rating, insulation, enclosure, regulation, core materials. Filament transformers, anode transformers, inductors, low frequency response, audio amplifier transformers. In audio work, the ratio of two voltages, E1 and E2, is usually stated in decibels according to the definition dB equals 20 log 10 E1 on E2. Amplifier voltage gain, transformer ratio, frequency response, and noise levels all may be expressed in decibels. If volume or voltage or power is given in decibels, it must be compared with a reference level, otherwise the term is meaningless. Transmission lines at audio and higher frequencies have properties commonly ignored at 60 cycles. Such entities as line wavelength, characteristic impedance, and attenuation are important at audio frequencies. Of particular importance is impedance matching. If a transmission line has no attenuation, its characteristic impedance is ZO equals the square root of L on C. If such a line terminates in a pure resistance load equal in ohmic value to ZO, all the power fed into the line appears in the load without attenuation or reflection. This process is called matching the impedance of the line. The notion has been extended to include the loading of vacuum tubes, but this is stretching the meaning of the term matching. The major problem of audio transformer design is obtaining good frequency response or constant voltage ratio over the required audio frequency range when the transformer is operated with the audio apparatus for which it is intended. Several factors outside the transformer affect its performance. 1. Impedance of the source of audio power. 2. Linearity of this impedance. 3. Impedance of the load fed by the transformer. And 4. Audio frequencies involved. Figure 13.18, the transformer In the figure 1318, the transformer that connects the audio source to its load may be represented by the diagram in figure 1319A. All right. Low frequency response, high frequency characteristics, harmonic distortion, doesn't really say what they think high and low frequencies are. Wasn't jumping out at me anyway. Calculation of inductance and capacitance, pentode amplifiers, modulation and driver transformers, shielding, audio oscillator transformers, decibel line carrier transformers, air core transformers, video and pulse transformers, pulse transformer core material, sawtooth transformers, blocking oscillator transformers, and references. Chapter 14, Vacuum Tubes as Circuit Elements by W.E. Shoup. The operation of a vacuum tube with load, amplifier with reactive load, analytical design equations for triode power amplifiers, vacuum tubes as variable impedance elements, variable inductance circuit, the vacuum tube as an electronic switch, references. Chapter 15, Rectifier Circuits, H.J. Bishel. A rectifier is an asymmetrical conducting device for protecting unidirectional current from alternating current. Several different types of rectifiers now in use include the electronic, copper oxide, selenium, and mechanical rectifiers. The electronic rectifier has grown in popularity not only in the supply of small quantities of direct current for the operation of radio receivers, transmitters, and industrial electronic equipment, but also for supplying large amounts of direct current for the electric railways, mining equipment, electrochemical processes, and for general industrial use. General considerations: the basic rectifier. A rectifier consists of a transformer and the rectifying element, such as a tube or a copper oxide unit. The transformer is used to step up the AC supply voltage, to step the AC voltage up or down to obtain the desired DC output voltage from the rectifier. The transformer also isolates the rectifier output from the AC supply. The rectifying element conducts current in only one direction and thereby produces a pulsating DC voltage across any load connected to the rectifier output. A simple rectifier is shown in figure 15.1. Ripple, loads, utility factor, single-phase half-wave rectifier circuit, single-phase full-wave rectifier, double-way full-wave rectifier, voltage doubler rectifier, three-phase rectifier. Oh, look, there's some notes in here. Someone's written in CT, bridge, and bridge. Oh, there we go. So they're talking about bridge rectifiers. Very interesting. Someone made some notes in the book. Three-phase Y double-way rectifier. The six-phase rectifier. Six-phase double Y rectifier. Grid-controlled rectifiers. Current overlap and commutation. Voltage regulation. The output voltage of the rectifier decreases as load current increases. This is caused by 1. Copper loss in the rectifier transformers, 2. Reactance in the rectifier transformer, and 3. Voltage drop in the rectifying elements. Gee, they phoned it in for the references. Only 2 references in this section. Chapter 16, Amplifier Circuits. Reuben Lee. An amplifier is a device for increasing voltage, current, or power. The original waveform may or may not be maintained. The frequency usually is. An amplifier may be mechanical, electromechanical, electromagnetic, or electronic, or a combination of these. The electronic amplifier circuit usually consists of a vacuum tube in conjunction with capacitors, transformers, or resistors. Input voltage or current is impressed on some element of the tube, and higher voltage or current is the output in the output circuit results. Amplifier potentials, transformer coupled amplifiers, tuned amplifiers, amplifier classification. Amplifiers can be divided into classes according to their mode of operation, following a standard definitions for these classes. Class A amplifier. A Class A amplifier is an amplifier in which the grid bias and alternating grid voltages are such that plate current in a specific tube flows at all times. Note, to denote that grid current does not flow during any part of the input cycle, the subscript 1 may be added to the letter or letters of the classification, class identification. The subscript 2 may be used to denote that grid current flows during some part of the cycle. Class AB amplifier. A Class AB amplifier is an amplifier in which the grid bias and alternating grid voltages are such that plate current in a specific tube flows for appreciably more than half but less than the entire electrical cycle. Class B amplifier. A Class B amplifier is an amplifier in which the grid bias is approximately equal to the cutoff value, so that the plate current is approximately 0 when no exciting grid voltage is applied, and so that plate current in a specific tube flows for approximately 1/2 of each cycle when an alternating grid voltage is applied. And then there's the Class C amplifier. A Class C amplifier is an amplifier in which the grid bias is appreciably greater than the cutoff value, so that the plate current in each tube is 0 when no alternating grid voltage is applied. Pardon me. And so that plate current flows in a specific tube for appreciably less than 1/2 of each cycle when an alternating grid voltage is applied. Classes A, B, and C are illustrated in figure 16.4, in which the alternating components of plate current, plate voltage, grid voltage, and grid current are shown with the steady or average values, which are respectively IB, EB, EC, and IG. Relative plate and grid voltage amplitudes for these 3 types of amplifiers are shown in figure 16.4, and typical properties are summarized in table 16.1. I'm not going to look close to that. Anode characteristics. Tube capacitance. Direct coupling, amplifier stability, grid bias, inverse feedback, distortion, cathode follower, modulation, automatic gain control, demodulation, frequency multiplication and division, and a couple of references. Chapter 17, Circuits for Oscillators, E.U. Condon and William Altar. An electronic oscillator is a device employing electronic tubes and associated circuits fed from a power source, usually a constant potential supply, and delivering AC energy to a load, Many different forms of oscillators have been developed to take care of the varying performance requirements. Magnitude of power output, magnitude of frequency generated, frequency stability, mode of operation, feedback oscillators, negative resistance oscillators, relaxation oscillators. No sharp dividing line distinguishes this class from the others. The term usually refers to oscillators in which the electrical condition changes abruptly and cyclically from one unstable condition to another. For example, the capacitor being charged through a resistor and shunted with a glow tube. As the voltage across the capacitor reaches the ignition voltage of the glow tube, the latter breaks down abruptly and discharges the condenser until its voltage is low enough to permit the glow tube to recover, whereupon a new cycle sets in with charging current flowing again to the capacitor. Electron transit time oscillators, general principles of feedback oscillators, circuits for feedback oscillators, Hardley A and B, Colpitts C, Meissner D, tuned plate E, tuned grid F, tuned plate, tuned grid G. Design of power oscillators. Okay. Oh, there's all the things that we're talking about earlier. Hartley, Colpitts, Meissner, tune plate, tune grid, tune plate, tune grid. All right. Power oscillators. Push-pull circuits. Piezoelectric crystal oscillators. Magnetostriction oscillators. Negative resistance oscillators. Relaxation oscillators. References. Chapter 18, Circuits for Industrial Control. H.J. Bishel. High vacuum tube circuits. Many control signals from indicating elements such as phototubes, strain gauges, and similar devices are at low voltage or power level. High vacuum tubes are used primarily to raise the voltage or power level of the signal. Designers tend to use thyrotrons as amplifiers wherever possible because of their greater power capacity and their relay action. But thyrotrons require large swings of grid voltage to bring about positive operation, and the signal may have to be amplified with high vacuum tubes. In comparison with radio application, industrial applications of vacuum tubes are quite different. Industrial control. Industrial control applications seldom require radio frequency. The use of amplifier tubes by industrial circuits can best be studied by considering the type of signal input, the desired form of the output, and the desired amplifier characteristics. Type of signal, desired form of output, desired characteristics, basic phanetron circuits, basic thyrotron circuits, Thyrotron operation with unidirectional anode voltage, Thyrotron operation with alternating anode voltage, bias supplies for control circuits, phase shifting circuits, resistance inductance phase shifter, resistance capacitance phase shifting circuit, capacitor transformer phase shifting circuit, electrically controlled phase shifting circuits, impulse generating and peaking circuits, an AC peaking transformer, timing circuits, ignitron circuits, operation in AC circuits, operation in DC circuits. References. Chapter 19, Transmission Lines by E.U. Condon and William Alter. Transmission lines commonly used in radio frequency electronic work are almost always of lengths comparable to or long compared with a quarter wavelength. Distributed inductance and capacitance in the line have pronounced effects at these frequencies. Although the fundamental theory is the same for both electrically long and short lines, the practical problems are much different from those encountered on power transmission lines. At 60 cycles, a quarter wavelength is 776 miles, which is considerably more than the longest transmission line in service. Yeah, right. Basic equations of a two-conductor line, propagation constant, characteristic impedance. In order that a wave may progress without reflections in accordance with equations 19.3 and 19.4, the ratio of the voltage to current must be the same at all points Z of the line. This ratio is called the characteristic impedance Z0 of the line. It can be computed for Z equals 0 in terms of the characteristic line parameters RLGC by examining gamma from equations 19.5 and 19.6. Pretty sure that's gamma. Yeah, that's gamma. So the characteristic impedance is this monster. If a transmission line, instead of extending to Z equals infinity, is terminated in a load of impedance ZO, I don't know how you pronounce the characteristic impedance, Z0, Z0, I don't know. No reflection will originate at the termination. The characteristic impedance, generally a complex quantity, becomes real only if LG equals RC, which is the condition for a distortionless line. Unless the characteristic impedance is real, voltage and current are not strictly in phase in a simple damp progressive wave. The simplest example is a radio frequency line with negligible losses, for which the characteristic impedance becomes real and equal to the square root of L on C, ohms. Characteristic impedance is expressed in ohms, not ohms per unit length, and refers to the impedance at input terminals of a line of infinite length. The most important practical two conductor lines are parallel wires and coax cable. Transmission line with load, propagation of modes other than the principal mode, transverse electric TE modes, transverse magnetic TM modes, measurement and evaluation of standing wave patterns, circular transmission chart. Oh, I've seen this before. Circular transmission chart with impedance contour lines. Power transfer and standing wave ratio. Short resonant lines. Problems illustrative of use of the chart. Transmission theory, a corollary of field theory. Alright. And then we've got references. Not many, couple. 5. Chapter 20, Antennas, T.M. Bloomer. An antenna is a system or structure for radiating or receiving radio waves, exclusive of the means for connecting its main portion with the associated apparatus. More simply, an antenna is a device for radiating or receiving electromagnetic waves. Antennas are used for many purposes, such as point-to-point communications, broadcasting systems, direction finding systems of mensuration, transmission of power, on an experimental basis, radar, LORAN, and other systems. Design is influenced by many factors. In broadcasting, for example, radiation should be concentrated in a given region for economic reasons, sometimes to minimize interference with stations on the same or nearby frequency. Energy must be radiated in a specified direction at a level too low to cause interference. A receiving antenna may utilize directional characteristics to increase the voltage of the received signal applied to the terminals of the receiver, and to discriminate against noise from origins not in the same direction as the transmitter. Another important factor is the ratio of the bandwidth to be radiated or received to the magnitude of the carrier frequency. Antenna impedance should be in the range where matching networks are reasonably efficient, unless efficiency of the system is relatively unimportant. The antenna must be designed so that it can be built from available material. Specifications should describe carrier frequency, power to be radiated, required field pattern, bandwidth, permissible impedance range, maximum permissible dimensions, maximum weight allowable, and any special features. Some of these specifications are affected by economics. For example, it is sometimes less expensive to increase the power of the transmitter or the gain of the receiver than to increase antenna gain by decreasing the angle of radiation of the antenna. There are two approaches to obtaining quantitative data for design. One is trial and error, and two is mathematical computation. The computation may be based on fundamental laws of physics and on assumptions. The accuracy of the conclusions depends on the accuracy of the assumptions. Maxwell's equations, theory of radiation. Got Ampere's law, Maxwell's equations. Induction. Let's see what they have to say about Maxwell's equations and equations 30.6 and 20.7 and 20.8 are the basic equations of electromagnetic theory. They are given here not for use but to show that the natural laws involved are known. Equation 20.6 is a form of Ohm's law. Equation 20.7 is the mathematical way of saying that a line of magnetic flux is a closed loop. Equation 20.8 states that a line of electric flux must start and stop either at a charge or at infinity, and that the electric flux diverging from a volume is equal to 4 pi times the charge within the volume. It is known that there is a force on a unit magnetic pole in the region of a conductor carrying current. Measurements have been made to establish the magnitude and direction of the force. The relation has been extended to include the effect of capacitors. H is known in terms of J and D, and if E is changing, and H exists. Faraday's law says that a changing magnetic field sets up a voltage in any circuit linked by the magnetic flux. Maxwell applied the Stokes theorem and found that a changing magnetic field induces an electric field. The solutions to Maxwell's equations, particularly for free space, represent traveling waves, and Maxwell was thus able to show the existence of electromagnetic waves. Induction field, induction field, radiation field. Elemental oscillating doublet. Linear antennas. Okay. Images. In considering the effects of the ground on the radiation In considering the effects of the ground on the radiated field at a point P in space, assume first that the Earth is a perfect plane reflector. Then at P there is a component of field from an elemental doublet along a direct path or ray, and another along a path involving reflection from the Earth's surface. I don't really know what a doublet is. What's a doublet? I don't know. I'll go look it up. I'll see if I can find out. So a doublet's just a type of antenna, and it's a dipole is a type of doublet. Basically, they've got a center feed and then two equally equal lengths for the other part. All right. Vertical radiators, self-impedances, base impedance of base insulated vertical radiators, antenna height, base impedance of top-loaded vertical antennas, mutual impedance, driving point impedance, current distribution, directivity, interference phenomena, time and space phase. Space phase. Theorem of reciprocity. Tell us about that. Any four-terminal network composed of linear bilateral impedances can be duplicated as far as external behavior at any one frequency is concerned by an equivalent T network. Dipoles. One of the simplest and most widely used antennas is the dipole, an antenna composed of two straight conductors lying end to end along a straight line with a small space separating adjacent ends. The dipole is always fed at the center by means of a balanced feed system. Free space dipoles, radiated field, self-impedance, dipoles near the Earth or ground plane, horizontal dipole near the Earth, antenna height, vertical antennas near the Earth, vertical dipoles near the Earth, ground systems, straight wire antennas, long wire antennas, wave antenna, V antennas, rhombic antennas, loaded antennas, top-loaded vertical antennas or end-loaded dipoles, radiated field, base impedance, sectionalized antennas, loop antennas, low-frequency loops, transmitting, receiving, high-frequency loops, driven directive arrays, arrays of arrays, arrays using reflecting surfaces, plane reflectors, Krauss antennas, I don't know how to pronounce, parabolic reflectors, parasitic arrays, parasitic antennas, dimensions, broadband systems. Many systems require broadband antennas. Television, for example, requires a good impedance match over a wide range of frequency. Sometimes it is desirable to have one antenna that will perform over a range of carrier frequencies. The major problem is maintaining a good impedance match to the line from the transmitter. Usually the best plan is to use an antenna of inherent broadband characteristics. Another plan is to utilize corrective networks in the coupling system. Dipoles again, antennas of special shapes, propagation of radio waves, factors affecting propagation, conductivity of Earth along a propagation path, dielectric constant of Earth along a propagation path, conducting layers called the ionosphere in the upper atmosphere, Earth's magnetic field, refractive index of the atmosphere, absorption of the atmosphere, diffraction, reflection. Not all factors are independent. Reflection at the Earth's surface involves Earth conductivity and dielectric constant for the region of reflection. Propagation at frequencies below the broadcast band. Propagation for the broadcast band. Propagation at frequencies from 1600 to 30,000 kilocycles. That's a lot. Propagation at frequencies above 30,000 kilocycles. Appendix 1. An example of impedance and phase shift calculations for an array composed of 3 vertical radiators. All right. Appendix 2. Analysis of current distribution in a tower radiator. General requirements of rectifier applications. C.R. Markham. The American Institute of Electrical Engineers has proposed the following definitions of rectifying device, rectifier, and rectifier unit. 1. A rectifying device is an elementary device consisting of one anode and its cathode, which has the characteristic of conducting current effectively in only one direction. 2. A rectifier is an integral assembly of one or more rectifying devices. 3. A rectifier unit is an operative assembly consisting of the rectifiers, the rectifier auxiliaries, the rectifier transformer equipment, and the essential switchgear. Rectifying devices and rectifier units have been developed to meet the requirements of specific applications. The high cost of development and the economy of mass production necessitate that as few types of rectifying devices and rectifier units as possible be used to meet the requirements of all rectifier applications. For this reason, it is the usual practice to choose the rectifying device and the rectifier unit for an application from existing designs. Table 21.1 lists various types of rectifying devices and some of their most common applications. Alright, so this is table 21.1, electronic rectifying devices and their applications. Alright, so we've got the Kenotron, which is a thermionic cathode vacuum diode. Application, low current, high voltage. Examples, X-ray, electrostatic precipitation. Alright, well I won't go into all the details, but we've got the rectagon, the tungar, the phenotron, and the thyrotron. And it's diode, and then triode or tetrode. Oh, and then there's even more down here. But they're not diodes either. Thermionic cathode vacuum tubes. Thermionic cathode gas tubes. Rectagon, tungar, phenotron, thyrotrons. They were mentioned as a bit of a favourite earlier, weren't they? Pool cathode gas tubes. Multi-anode versus single anode rectifying devices. Sealed versus pumped rectifiers. At the present time, sealed rectifiers are generally used for the lower ratings and pumped rectifiers are used for the larger ratings. The type of equipment recommended depends upon the application. Chapter 22. Mercury arc rectifiers for power application. G.F. Jones and C.R. Markham. Relationship of characteristics to application. Arc back. In a mercury arc rectifier, the direction of current is from the anode to the electron-emitting cathode spot and in that direction only. Although current is in the direction of electron travel, it is universally accepted that the direction of current is in the opposite direction from anode to cathode. Current direction can be from cathode to anode if a cathode spot is formed on the anode. This condition is known as arc back, and we heard about that earlier. So it's a little gremlin in the tube technology. Not a problem for us these days. Sounded like it was a bit of a hassle. Parallel operation, regeneration, overload, current relations, voltage surges, noise and vibration, harmonics, telephone interference, generator heating, associated apparatus, transformers, switchgear. They talked about switchgear earlier with the rectifiers. Switchgear for a rectifier unit is designed to start and stop the unit and to give it adequate protection under abnormal conditions. Yeah, right. Excitation system. For a second there, I thought that was a program, but of course they didn't have programming in 1948, did they? I don't think they did. Maybe they did. I don't remember. Vacuum equipment. Efficiency, power factor, regulation, phase control of output voltage. References. Chapter 23, Inverters. J. L. Boyer. The conversion of DC power to AC power by electronic. The conversion of DC power to AC power by electronic equipment can be accomplished by either an oscillator or an inverter. These two terms usually are applied to definite types of conversion equipment. A device using vacuum tubes or rectifying elements in which the flow of current through the elements is controlled continuously is called an oscillator. A device using gaseous tubes or rectifying elements in which only the start of current conduction can be controlled is called an inverter. The characteristics of these two types of converters are different, and therefore each has its own field of application. Only the inverter is considered in this chapter. The inverter is applied where highly efficient static equipment is required and where the output AC frequency is not above that at which gaseous tubes can be controlled. Ratings from a few watts to thousands of kilowatts can be obtained with the designs of gaseous tubes which are now available. The normal lower frequency limit is in the low power frequencies and can be as low as is practical for the transformer equipment. The tubes may have an extremely low frequency limit, and some types can conduct a continuous current. The upper frequency limit is from 2,000 to 3,000 cycles per second, which is about the practical frequency limit for which mercury vapor gas tubes can now be designed to control the forward currents. All right, got inverter operation. Classification of electronic frequency converters. That's kind of interesting, isn't it? All right, so we've got AC to DC as a rectifier. DC to AC is an oscillator or an inverter. DC to DC is not covered. AC to AC, single conversion, double conversion. Okay. And then they join up down here, and then you've got self-excited, separately excited, parallel capacitor, series capacitor, compound capacitor. Wow. Separately excited inverter. Commutation requirements, rating, frequency limitations, self-excited inverters, parallel capacitor inverter, capacitor requirements, application, series capacitor inverter, compound capacitor inverter, special circuit conditions, inverter faults, arc through, forward fire, misfire, incomplete commutation, arc backs on inverter tubes. Arc backs are sometimes found to occur in inverter operation, but they are not serious by themselves since the circuit voltages do not maintain reverse current in the tubes. The arcback may come at the end of the conduction period in the short angle when the anode is negative. The important disadvantage of the arcback is that it usually becomes an arc through because there is considerable ionization in the tube when the anode goes positive. Clearing inverter faults. Application of inverters for regenerative loads. Reversing DC motors. Rectifier and inverter frequency changer. Characteristics, applications for electronic frequency changes, single conversion electronic frequency changer, circuit operation. This is the cycloconverter, circuit operation, applications, cyclorectifier, cycloinverter, self-excited cycloinverter for induction heating, frequency limits, circuits, high frequency ignitrons, operation characteristics, DC transformer, DC transmission, constant current circuit, constant voltage circuit, commutation on receiving AC system, application, faults. Faults on a DC transmission line are of two types, those caused by short circuits on the line itself and those caused by the tubes. Most line short circuits would be caused by lightning, and with DC transmission there would be little possibility of the arc clearing itself. There is some evidence to indicate that DC transmission lines can have good arc extinction characteristics. The best results are obtained with an ungrounded midpoint, but the additional insulation required probably cannot be justified. Faults caused by arcbacks of the rectifier tubes and arc-throughs of the inverter tubes are not so severe as a complete short circuit on the transmission line. However, with the large number of high voltage tubes involved, it will be necessary to obtain tubes that have a low fault rate. Ignitrons for inverse and forward voltages up to 20,000 volts have high arcback rates compared with low voltage tubes. Since there are no fundamental limitations on the design of high voltage tubes, tube design will not be the type of limitation which would prevent the eventual perfection of DC transmission. In a DC transmission system, the faults would be cleared by means of arc quenching of the tubes so that the fault would be cleared in a short time and power flow could be restored in a matter of a few cycles. Usually the fault can be cleared in such a short time that no disturbance can be noticed. Radio frequency heating by D. Venable and T.P. Kin. Induction heating. Rotating machines supply induction heating power at frequencies up to 30,000 cycles per second and with power outputs up to several thousand kilowatts, with the exception that machines with frequencies above 10,000 cycles per second are limited in output. One rather new source of power for induction heating is the mercury arc frequency changer, which produces frequency as high as 3,000 cycles per second. Its frequency depends upon the number of phases used and the deionization time of the mercury arc. Spark gap oscillators are used for frequencies from 20,000 to 400,000 cycles per second. They are used for heat treating, surface hardening, brazing, and soldering. Power outputs as high as 35 kilowatts are available commercially, but the spark gap oscillator efficiency varies from about 50% under normal operating conditions to about 15% under poor conditions, depending upon the type of load, the method of coupling to the load, and the conditions of the spark gap. Badly burned gaps very seriously decrease the oscillator's efficiency. The vacuum tube generator can be used for frequencies from about 100 kilocycles to several megacycles per second for induction heating, with power output ranging from a few hundred watts to several hundred kilowatts. For thin case hardening, these higher frequencies are better than the lower frequencies produced by rotating machines. General induction heating for soldering, brazing, surface hardening, and annealing can be done with vacuum tube generators ranging in frequency from 200 kilocycles to about 5,000 kilocycles. So 500 kilocycles. A few special induction heating operations are done at about 15 megacycles per second. Dielectric heating, vacuum tube oscillators, frequency and power rating, symptoms of various loading conditions, induction heating theory, field equations, hysteresis loss, skin effect. Skin effect is the diminishing of current density from the surface to the inductor of a conductor carrying alternating current. To visualize this effect mathematically, in its simplest condition, a harmonically varying magnetic field above an infinite conducting plane is assumed. The conditions thus imposed facilitate the use of equations 24.3 to examine the current distribution in the region at and below the surface of this infinite conducting plane. The solution for an alternating magnetic field becomes Jx equals J0 epsilon to the power of minus alpha x, means nothing to me, where Jx represents current density at any point x units of distance below the surface of the plane, and J0 is current density at the surface of the plane. The first exponential term represents the decrease of magnitude of the current density Jx as the distance from the surface increases. The second exponential term describes the phase relation between the current on the surface and the current at any distance x from the surface. Depth of penetration, heating solid cylinders, heating hollow cylinders, proximity heating, application of induction heating theory, magnetizing force, coil design, coil loss dissipation, ampere turns per inch, load coupling, heat patterns and coil shapes. It's all pretty fascinating. I assume this is what's going on in your toaster, or maybe not. Transformers and current concentrators. Numerical examples: non-magnetic materials, heating iron to above magnetic transformation point, magnetic material, induction soldering, brazing, and heat treating, high temperature soft solders, fluxes for soft soldering, joints for soft soldering, silver brazing, silver solders, fluxes for silver brazing, design of joints for silver brazing, jigs and fixtures, induction soldering and brazing, heat treating, hardening, stationary hardening, progressive hardening, quenching, annealing, dielectric heating theory, properties of imperfect dielectrics, power absorption, measurement of dielectric properties, power requirements, dielectric heating applications, power density, voltage, and frequency, matching networks. To transfer power to a load in the best manner, the load impedance must be transformed into an impedance which can utilize available generator current and voltage most favorably. At power frequencies, transformers are used often. Actually, a transformer is a network consisting of reactive components with some losses. At high audio frequencies and at radio frequencies, the use of an iron core transformer for high power is limited by high core losses and stray reactances. At high frequencies, air core transformers are used more often. Their leakage reactance is large, which implies that regulation is poor. Power transformers for the megacycle range of frequencies are not generally used to couple dielectric heating loads directly to a radio frequency generator, but a generator can be coupled to a transmission line by means of an air core transformer. An impedance arrangement can be used in place of transformers as a means of transforming a load impedance. To minimize losses or increase efficiency of such a network, its elements are made as nearly pure reactance as is economically justified. The types of networks considered here are those reducible to the 4-terminal network shown in Figure 2483. Examples of dielectric heating: plastic preforms, plywood bonding, rayon drying, economics of high-frequency heating. Typical industrial application: induction heating, some pretty interesting photos here. Figure 24111, induction melting of special steel alloy, courtesy of Ajax Electrothermic Corporation. And then we've got induction heating furnace installation. Wow. Induction heating forge shop. Induction heating gun tube with 9,600 cycles. Low frequency induction brazing. High frequency induction soldering of capacitor cans. Brazing flanges to ends of tube. Continuous heat treating of bar stock with rotating machine frequencies. Crankshaft hardening with rotating machine frequencies. 30-inch diameter, 6-inch face, 1.5 pitch sprocket contour hardened using 9,600 cycles. Wow. It's amazing. Finished pre-washed mattress. Got a table here. Physical and electrical constants of metals. Got the metal and then its resistivity in micro-ohm centimeters, temperature coefficient of resistivity, specific gravity, specific heat, thermal conductivity. Characteristics of dielectric materials. Chapter 25, Power Line Carrier. F.S. Mabry. Power line carrier is the application of high-frequency carrier currents to power transmission lines. These high-frequency currents are usually in the frequency band from 50 to 150 kilocycles. The term carrier implies that the high-frequency wave is modulated or varied proportionally by the signals to be transmitted. By using carriers of different frequencies, many carrier circuits or channels may be established over a single wire or pair of wires. These channels, as they are most generally called, are used for telephone communication, relaying, telemetering, load control, supervisory control, and remote tripping. Reliability of these services is limited only by the reliability of the power line itself and of the carrier terminal apparatus. Before the development of the power line carrier, it was necessary to use telephone wire lines for these functions. They were generally less satisfactory than power line carrier for several reasons. Wind and sleet, which will completely carry away a telephone line, do no great harm to a power line because of its sturdy mechanical construction. Telephone lines owned by power companies generally parallel high voltage power lines and sometimes are subjected to noise and induction, which may cause improper functioning of the apparatus. It is difficult to protect apparatus and personnel against the hazard of high voltage in the telephone wire line caused by induction or accidental contact between the telephone and the power lines. Because of the inherent advantages of using the power line itself as the conducting medium for communication or control circuit, the application of power line carrier should be thoroughly understood and fully exploited. Yeah, right. That technology didn't really come to be, did it? I think they do use it though. I think that your off-peak equipment is sort of controlled by, like your hot water heater, controlled by the electric company, and they use their power lines to control it. There's some sort of protocol. I don't know. Carrier communication, types of modulation, amplitude modulation, frequency modulation, single sideband modulation, carrier relaying, telemetering, carrier load control, carrier supervisory control, transmission losses and gains, the transmission line, methods of line coupling, characteristic impedance. That's our old Z0 again. I don't know how to pronounce it though. Line losses, effect of tap lines. I'll see if I can figure out what they call Z0. Hang on. Alright, so my sources are telling me it's Z0. Z0 is the characteristic impedance. Z0. Line losses, effect of tap lines, the coupling capacitor, the line tuning unit, the line trap, bypasses, spectrum utilization, references. Chapter 26, Electronic Instruments, MP4. For measurement of simple single quantities such as potential, current, time, and frequency, mechanical and electromagnetic instruments are available. Within their operating ranges, these are accurate and reliable. Electronic instruments should be considered to supplement them, not replace them. If the power available for operation of an instrument is minute, the amplifying properties of electronic tube make it possible to design an instrument that does not unduly disturb the circuit to which it is connected. In other cases, because of the lack of inertia of electrons or the rectifying properties of electronic tubes, together with their small inductances and capacitances, electronic instruments can be made to operate at higher frequencies or over a broader range of frequencies than more conventional instruments. More complicated electronic instruments such as the electron microscope, mass spectrometer, and dynamic balancing machine exist because their functions are so fundamentally electronic that they cannot be performed by a non-electronic device, or because the use of electronics results in a less expensive, more flexible, or more easily operated unit. Electronic instruments are widely used in all fields of research, in many types of testing, and in an increasing number of routine manufacturing operations. In this chapter, the more common electronic instruments and their fundamental operating principles are described as an aid in applying the proper instrument to the job at hand. The reader who wishes to construct instruments and who needs detailed design information is urged to make use of the technical articles listed at the end of the chapter. Vacuum tube voltmeters, logarithmic voltmeters, slide back voltmeters, transfer characteristic voltmeters, anode detection voltmeters, electrometers, electronic microammeter, sensitive electrometers, electrometer tubes, theory of compensated circuits, measurement of high resistance by means of an electrometer, high frequency ammeter, frequency meters, primary frequency standards, fundamental standards, accuracy, alternative frequency standards, standard frequency sources, comparison of frequencies, heterodyne frequency meter, cathode ray oscilloscope. Two rather simple methods of comparing frequencies by means of a cathode ray oscilloscope have been devised. One consists of impressing the known frequency on the horizontal deflecting plates of the oscilloscope tube and the unknown frequency on the vertical deflecting plates. The known frequency is adjusted until a stationary pattern appears on the oscilloscope screen. This pattern is known as the Lisiduous figure. I don't know how to pronounce it. When the pattern is stationary, the ratio of the unknown frequency to the known frequency is the ratio of the number of times the Lisiduous figure is tangent to a horizontal line to the number of times it is tangent to a vertical line. Figure 2618 is a Lisiduous figure obtained when the ratio of the frequency on the vertical deflecting plates to that on the horizontal deflecting plates is 3:2. This method of comparing frequencies is extremely simple and is essentially as accurate as the adjustable known frequency. If large numbers are involved in the ratio of unknown to known frequency, however, and if either the known or unknown frequency contains appreciable amounts of higher harmonics, the Lisiduous figure becomes too complicated to be analyzed easily. If the ratio of frequency is large, say 10 or so, it is convenient to split the phase of the lower frequency by means of a resistor and capacitor. The two voltages with a 90-degree phase separation thus obtained are applied to the deflecting plates of an oscilloscope tube to produce a circle or broad ellipse on the screen. The higher frequency is superimposed on the positive potential applied to the accelerating anode of the oscilloscope tube. This causes the velocity of the electrons in the beam to be alternately increased and decreased from its mean value. Okay. Frequency determination from capacitor charging current. Bridge circuits for measuring frequency. The Wien bridge. Bridge circuits fundamentally are not electronic, although electronic amplifiers are often used to aid in detecting balance. Fundamentally, any bridge circuit for which frequency appears in one or both of the balance equations can be used for measuring frequency in terms of the known impedance impedances of the bridge arms. One of the simplest and the best of these circuits is the Wien bridge, shown in figure 2623. Provided that the relations between the circuit elements are as shown on the diagram and that R prime resistance is 0, the balance equation of the bridge is F equals 1 on 2RAC. Bridge design, grounding of bridges, networks for frequency measurement, tuning for maximum secondary current, tuning by grid current dip, design considerations, ultra high frequency meters, calibrated transmission lines, theory, spurious effects, shortening of the line, precise measurements, resonant cavities, time interval and speed meters, methods of measuring time intervals, synchronous clocks, change of charge on capacitor, cathode ray oscilloscope, design of time interval meters, methods of actuating trigger circuits, stroboscopes, application of stroboscope, motion study, dynamic balancing, measurement of frequencies, light characteristics, effects of stroboscopic illumination, stroboscopic light sources and control circuits, glow lamp, neon filled thyrotron, the strobotron, strobotron firing circuit, low pressure arc. The most brilliant flashes of light of shortest duration are obtainable with a simple glass tube with electrodes sealed in the ends and filled with neon or mercury vapor at a reduced pressure. Action of arc tubes. Cathode ray oscilloscope. The cathode ray oscilloscope is probably the most versatile and most widely used of all electronic instruments. It is widely used in industrial measuring equipment and in testing equipment of various kinds. Function of an oscilloscope. Cathode ray tube, fluorescent screen characteristics, special purpose oscilloscope tubes, deflecting amplifiers, amplifier frequency range, amplifier output circuits, attenuators, sweeping circuits, use of oscilloscope, measurement of amplifier gain, phase and distortion measurement, modulation measurement, frequency response measurement, bridge balance indication, transmission lines, coil testing, study of transients, frequent transients, infrequent transients, time delay circuits, balancing machines, unbalance in rotating bodies, balancing machines, the wattmeter method of vibration measurement, calculation of unbalance correction, compensation for original unbalance, amplifier design, stroboscopic light source, extraneous vibrations, precision balancing, combination wattmeter and stroboscope balancer, amplifier and filter system, extraneous vibration caused by aerodynamic disturbances, fatigue testing equipment, fatigue of metals, factor of safety, endurance limit, fatigue testing equipment, vibration motor, amplifiers, self-excitation, elimination of unwanted modes of vibration, control of amplitude of vibration, amplitude of fatigue testing equipment. Sorry, that's not amplitude. Application of fatigue testing equipment, determination of natural frequencies, testing non-resonant specimens, limitations of fatigue testing equipment, the mass spectrometer, history of the mass spectrometer, principles and of design and operation, the 180-degree mass spectrometer, comparison with mass spectrometer, applications of the mass spectrometer, fundamental research, industrial applications, petroleum refining. Crude oils consist of a mix of hydrocarbons ranging from the simple gas methane to highly complex molecules containing 45 or more carbon atoms. In general, the substances of lighter molecular weight are more volatile than the heavy compounds, These substances can be separated by distillation to yield illuminating gas, naphtha, gasoline, light and heavy lubricating oils, and residues of paraffin and asphaltic oils. Because the economic demand for petroleum is not on the same proportion as their natural occurrence, the heavier molecules are cracked to increase the yield of the lighter gasoline and lubricating oil constituents. The results of each step of the cracking process depend upon several variables. To assure the desired outcome, the various stages of the process must be monitored by chemical analysis. Conventional chemical analysis is sometimes too slow to be useful. Faster methods of analysis by means of infrared spectroscopy are used for some analyses, and the mass spectrometer provides a rapid method for others. Synthetic rubber manufacture, chemical analysis with the mass spectrometer, calibration, mass spectrometer design, tube, extraction of ions, filament structure, collection of ions, gas absorption, adsorption. Sample introduction system. Valves, electrometer, rectifiers, magnet power supply, filament emission regulator, electron potential supply, mechanical arrangement, present limitations and future possibilities, analyzable substances, calibration, accuracy of analysis, the electron microscope, applications of the electron microscope, medicine, chemistry, engineering, lubrication, engineering corrosion, principles of operation, magnification and resolution, limitation of resolution by diffraction, the quantum theory. According to the quantum theory, the smallest possible quantity of electromagnetic energy is W equals hv, where h, the Planck's constant, at 10 to the minus 27 erg seconds, and v is frequency in cycles per second. All right. Electron wavelength, comparison of light and electron wavelengths, history, construction, limitations and techniques, effective vacuum on the specimen, specimen thickness, measurement of object height, calibration, limit of resolution, high voltage microscopes, magnification, depth of focus. Chapter 27, Industrial X-ray Applications. D. E. Morgan and F. A. Trenkel. The discovery of X radiation by Professor W. C. Rontgen in 1895 touched off speculation as to its exact nature and that of the entire electromagnetic radiation spectrum. At present, the wave mechanics theory seems to satisfy the observed phenomena, but in this chapter, it is convenient for some purposes to ascribe continuous wave characteristics to the radiation. For other purposes, it is advantageous to consider the radiation as being composed of discrete bundles or photons of energy. This consideration need not lead to confusion, for the two concepts do not conflict in the applications considered here. In general, the commercially important X-ray applications can be divided into two classes, medical and industrial. Medical applications include diagnosis or treatment of human or animal ailments and studies of the effect of X radiation on living organisms. Industrial applications necessarily include some which physicists or chemists may believe should not be in this category. Figure 27.1 shows that such an arbitrary division is not entirely adequate. For example, photochemistry and radiobiology overlap greatly, even though they have been placed in different groups. In this chapter, the discussion of industrial uses of X radiation includes the objectives of use, the particular applications which have proved successful, and a description of the equipment used. At the end of the chapter is a general discussion of the objectives and the equipment used in its medical work. Economics of gross structure examination. Welding industries, other industries, fundamentals of application, X-ray generators for gross structure examination, 0 to 50 kilovolt class, 50 to 100 kilovolt class, 100 to 150 kilovolt class, 150 to 300 kilovolt class, 300 kilovolts and above. Ultra high speed radiography, technique of gross structure examination, industrial radiography, industrial fluoroscopy, industrial photofluorography, non-visual recording, electrical resistivity, ionization, multiplier photocells, microradiography, examination of fine structures, experimental diffraction methods, photochemistry, medical X-rays, medical fluoroscopy, medical photofluorography, therapy. The radiologist utilizes the fact that some abnormal growths are more sensitive to radiation than are normal tissues. For example, an equal quantity of radiation absorbed by a cancer growth and by normal tissue will eventually kill the cancer tissue, but the normal tissue will recover. Even various normal body tissues react differently to radiation. The quality of the X-ray beam, as determined by tube voltage, is manipulated to concentrate as much of the energy as possible at the part of the body to be treated. For penetrating deep into the body tissues, a high voltage is used, and for surface disorders, a low voltage is needed. The patient is irradiated from many angles. The point to be treated is always concentrated on, but the patient is moved between treatments so that the radiation enters the body through different areas on the skin, and therefore the skin dose is kept as low as possible. Radiogenetics, and then references. Chapter 28, Electrostatic Precipitation, by E.H.R. Pegg. Electrostatic precipitation had its beginning in 1824 when Hohlfeld observed that a corona discharge had a cleaning effect on dust-laden gases. Years later, Sir Oliver Lodge and, later still, Dr. Cottrell developed it into a practical form and made successive installations for the precipitation of smelter fumes and other industrial dusts. It has been recognized for many years as the outstanding method of removing fine, solid, or liquid particles from gases. This form of precipitator is limited in its uses, however, because its corona discharge generates so much ozone and oxides of nitrogen that the cleaned air is unsafe for human consumption. This result is due largely to the use of high direct potentials of 30,000 to 100,000 volts and high currents. In 1936, Penny announced the development of a new type of precipitator, which was smaller, required less voltage and power, and generated so little ozone that air cleaned by it could be used for ventilation. Such a device, marketed under the trade name Precipitron, made possible some applications of electrostatic precipitation that were not previously practical, such as the air conditioning or ventilation systems of commercial and public buildings. Analysis of electrostatic precipitation, separation of particles from the air, charging the particle, field charging, charging by molecular or heat motion, two-stage precipitator, efficiency of a two-stage precipitator, application of the precipitron air cleaner. A precipitron installation showing the air discharge side of the collector plates. Chapter 29, Electronic Motor Control. K.P. Puchlowski, I don't know. Electronic motor control represents one of the newest branches of industrial electronics. Although the first applications of electronic devices, or tubes, to control the performance of an electric motor were made in 1930, those early attempts were not too successful from the practical point of view and did not go much beyond the laboratory stage. However, recent developments and improvements in electronic motor control systems have created an ever-increasing number of new practical possibilities and have aroused considerable interest in industrial applications of electronic controls. The term electronic motor control implies in its broadest sense an electrical system consisting of an electric motor, combination of electronic elements or tubes, and a more or less complex network of control circuits. In recent years, however, the most significant engineering progress has been achieved in the field of electronic control of DC motors, and at the present time these DC motor systems have a much greater importance and practical usefulness than any of the existing AC motor systems. Consequently, this chapter will be devoted exclusively to electronic control of DC motors. Rectifier drives. Electronic DC motor controls operate on the principle of rectification. That is, a rectifier converter is always used to provide the direct voltages necessary to drive and properly control a DC motor. Thus, the term rectifier drive or electronic drive may be used to indicate that the motor is not only controlled electronically, but also that the power to it is supplied through electronic rectifying devices. DC motors with shunt excitation are particularly applicable as driving means for different industrial applications because of the well-known fact that speed of such motors can be readily varied by proper control of voltages applied to the armature and field windings. It must be realized, however, that the advantage of speed control characteristics of a DC motor cannot be fully utilized unless an adjustable DC voltage to be applied to the armature is available. On the one hand, the electric power available is about 90% of industrial establishments is of the AC type and cannot be used directly to drive a DC motor. On the other hand, even if a DC supply line were available, it would normally be of a constant voltage type and therefore only field control by means of a rheostat could be accomplished. Speed control below the rated or base speed of the motor by means of a rheostat in the armature circuit is not acceptable in industrial applications on account of prohibitive losses, size, and cost of the rheostat, and an excessively drooping speed torque characteristic for the drive. Thus, in order to take full advantage of a DC motor characteristic, it is necessary to provide an adjustable output voltage converter which would convert the AC line voltage into an adjustable DC voltage which is applied to the motor. The general trend is to increase the efficiency and speed of various industrial operations. This trend usually requires the application of individual converters to each driving motor in order to provide independent control, especially adapted to individual conditions. The very popular rotating converter consisting of an AC motor driving a DC generator and known as the Ward-Leonard system is one of the most widely used adjustable voltage supplies. The rectifier converter, combined with a complete electronic control and regulating system, represents a new method of industrial control. Its prime advantage over the rotating type of converters is that only one rotating machine is used instead of all of the 3 and often 4 rotating machines used in the other systems. In addition, the compactness of the electronic system, the flexibility for adaptation to various conditions, accuracy, and sensitivity are by no means of secondary importance. Rectifier drives can be divided into two general classes. One, systems where the alternating voltage is varied either by means of a variable ratio transformer or by means of a saturable core reactor, and then is rectified and applied to the armature of a DC motor. Single phase or polyphase rectifier systems may be used. The rectifying elements are either of the Fanatron or Rectigon tube type, or sometimes of the metallic type, such as copper oxide or selenium rectifiers. Although drives of this group may have some advantages, such as simplicity and low form factor of the armature current, they do not possess all the advantages of accuracy and flexibility of the drives of the second group. The second group includes systems in which both rectification and control are performed electronically by means of controlled rectifier tubes of the thyrotron or ignitron type. These tubes handle the power and operate in conjunction with electronic control circuits using high vacuum tubes of the so-called radio receiver type. Application characteristics of DC shunt motors, controlled rectification, characteristics of rectifier motor system, elementary systems for armature control, armature voltage regulation, armature voltage drop compensation, control of acceleration. Modifications of basic circuits for compensated drives, field rectifiers and control, electronic drive tachometer generator type, instantaneous peak value and form factor of the armature current, methods and principles of braking, rating efficiency and power factor, conclusions. In preceding sections, general principles of electronic motor control, and in particular of controlled rectification, were outlined. Several typical electronic control networks for rectifier motor systems were described to illustrate possible solutions of some fundamental control problems. It should be remembered, however, that no attempt was made to cover all the recently developed circuits, some of which still remain undisclosed. In addition, the scope of this chapter could permit the inclusion of only a few of the existing circuits. The control problems and the typical means for their solution dealt with in this chapter were approached from the point of view of an adjustable speed electronic drive for general purpose applications. In other words, specific application problems were not emphasized here, but only general elements of performance such as speed control, speed torque characteristics, control of acceleration, principles of rectification and inversion were given special attention. Many problems of considerable interest either could not be mentioned at all or had to be discussed very briefly. General purpose electronic drives and their main functions, which were given special attention in this chapter, represent only one group of the rapidly growing field of electronic motor control. In fact, the number of special electronic control systems and networks for rectifier drives is very great and includes various electronic control and regulating systems for every conceivable application involving control of motors. To mention a few, hoist and crane drives, small traction drives, drives and regulators for various winding operations, tension regulators, acceleration regulators, drives for stoker control, automatic cycle drives for machine tools, and drives with spindle load control for milling machines represent an active field for various electronic motor control systems. Chapter 30, Regulation. Regulation is the automatic process of maintaining a designated quantity at a predetermined value or of varying that quantity according to some prearranged plan. More specifically, the process is one of matching the designated quantity to a reference or pattern in a manner to maintain the smallest possible difference or error between the two. Regulation of voltage on a DC generator is a typical example. Here, all or a portion of the generated voltage is compared to a battery or other suitable constant reference voltage, and the difference between these voltages is amplified. A control device operating on the amplified error signal furnishes the required corrective means to make the error or difference voltage tend to approach zero. Regulation is a closed cycle process as contrasted to an open cycle control where the controlling element is in no way influenced by the controlled quantity. The fundamental difference between the two types of control is illustrated in the block diagrams of figure 30.1. Yeah, right. These days we'd call that open loop or closed loop. On-off type of regulator, dead zone regulator, proportional regulators. These days we have PID, proportional, integral, and derivative. Doesn't seem to have been a technique developed yet in this book. Generator voltage regulator, time delay and anticipatory operators, derivation of system equation, motor speed regulator, motor speed equation, mechanical time constant, derivation of system equation, speed measurement by counter electromotive force, speed regulation by motor field control, position regulator, derivation of system equation, regulator characteristics, solution of regulator equation, system stability and damping, stability criteria. It has been indicated in the preceding paragraphs that an inspection of the roots of the auxiliary equation of a regular system will reveal whether or not the system is stable. In many cases, however, it is desirable to know if a system is stable before the frequently long and involved calculations to determine the roots are performed. If the system is found to be unstable, there is no need to solve for the roots. Time can usually be saved if some change in the system which will ensure stability is sought before the roots are computed. Effect of system parameters on regulator performance, system amplification, system time constants, 2 delay system, system time constant, 3 delay system, anti-hunting circuits, anticipator circuit, feedback around amplifier and 1 delay, feedback around amplifier and 2 delays, alternative anti-hunting circuits, applications, multicolor press register regulator, speed regulator for wind tunnel drive, speed regulator for a sectional paper machine, electric arc furnace regulator. References. Chapter 31. Resistance welding control. C.B. Studham, E.T. Hughes, F.R. Woodward, and H.J. Bishel. In order to visualize properly the field of electronic control for resistance welding, an understanding of the fundamental theory and application of the welding process is desirable. On some work, electronic controls are not economically preferable, but in general, electronics has broadened the application and improved the quality of resistance welding to such a degree that it is considered indispensable to the process. Resistance welding is the process of joining two or more metallic parts to form an assembly, the heat for the formation of the weld being created by the resistance of the parts and welding machine electrodes to the passage of electric current supplied by the welding machine. Fundamentals. Spot welding machines, spot welding technique, spot welder sequence control, welding electrodes, seam welding, projection welding, button flash welding, timing, transients and their influence on welding, effect of power factor on transients, switching of welding current, asynchronous welding control, the electronic contractor, controlling current in the electronic contractor. Oh, that's not contractor, that's contactor. Contactor. The asynchronous spot welding timer, the asynchronous pulsation spot welding timer, timing the sequence of operation, sequence weld timer for spot welding, synchronous precision welding control, electronic contactor, firing means for synchronous control, heat control for the synchronous system, coupling the circuit for the synchronous system, synchronous precision spot timer, synchronous heat control circuit, synchronous pulsation counting circuit, sequence timer for pulsation spot sequence timer for pulsation spot timer, electronic seam timer, semi-electronic seam timer, energy storage systems, welding aluminium, the elementary capacitor discharge circuit, rectifier, charge control circuit, blocking circuit, discharge circuit, full cycle discharge system, unidirectional discharge system, forge timing circuit, flux resetting, magnetic energy storage for resistance welding. There we go. No references in this one. Chapter 32, Industrial Photoelectric Control by V.B. Baker. Application of light-sensitive control is logically divided into two groups. 1. Old jobs that can be done better or more economically by photoelectric control, and 2. Functions which were formerly impossible. To replace some existing device, photoelectric control must be justified on the basis of economy or its ability to give better performance, a better product, or higher production. If a task can be performed in several ways, the merits of each solution must be considered carefully. It is not so difficult to justify the use of photoelectric control to perform a function which cannot be done satisfactorily in any other manner. Any photoelectric device is vastly inferior to the human eye. Man has not yet made a device which can match certain abilities of the eye. For example, the eye does not have to be focused on a passing object, perhaps only a tiny speck, to be aware of its presence and direction of motion. No phototube has this ability. Much time and money have been spent on some photoelectric inspection jobs, such as the determination of surface flaw in paper and tin plate, or foreign material in milk and soft drink bottles, but success has been negligible. The solution of this type of problem may perhaps be found in the iconoscope and the methods of high-speed scanning used in television. Yeah, right. Phototube amplifiers. sensitivity, speed of response, optical systems, light sources, phototubes, applications, general control, alarms and safety devices, measurements, regulators. This photo is a photoelectric scanner of a slitter or side register regulator showing synchronous motor, rotating disc with 4 lenses, and phototube housing. This is a web scanner used on multicolor press showing light source, aperture, and photomultiplier tube all mounted in an explosion-resisting cabinet. Chapter 33, Applications of Ultraviolet Radiations by H.C. Rentschler. Many physical, chemical, and biological reactions are influenced by light, and particularly by ultraviolet radiation. In Chapter 10, lamps for producing radiation in the different regions of the ultraviolet spectrum are described. These lamps make possible numerous commercial uses of radiation, which were heretofore feasible only to a limited extent. Applications may be classified as photochemical reactions, bactericidal and fungicidal actions, biological effects, and excitation of fluorescence and phosphorescence. Photochemical reactions. Bactericidal and fungicidal actions. Radiation for destroying airborne organisms, surface irradiation, biological effects, excitation of fluorescence and phosphorescence, fluorescent lamps, identification of materials and adulterants. References. Chapter 34, Radar, Fundamentals and Applications, Hugh Odishaw. The principle of radar is the reflection of electromagnetic energy from an object in its path. The analogous behavior of sound and light waves affords a somewhat more familiar illustration of the phenomenon. Microwaves, radiations of wavelengths ranging from a few millimeters to several centimeters, behave much like light waves. Seeing depends upon reflection of light from the object to the eye. Detection of distant objects by radar likewise depends on reflection of high-frequency radio energy. This principle is useful because electromagnetic waves are propagated at a constant velocity of about 3 times 10 to the power of 8 meters per second. Reflection of energy usually indicates the presence of a target within range of the system, and because the velocity is constant, the target range can be measured by the lapse of time between the transmission of a signal and reception of its reflection. Finally, electromagnetic waves travel in straight lines like light rays. Therefore, the elevation and bearing of the target can be measured because the angular position of the radar antenna with respect to some reference plane coincides with the angular position of the target. Rotation and tilting of antennas is incidental because the ratio of these velocities to the velocity of light may be considered to be zero. Although electromagnetic waves travel essentially in straight lines, shorter waves are preferable to longer ones for several reasons. Shorter waves can be more conveniently beamed. Beaming is a prerequisite for precise determination of bearing and elevation. Waves at broadcast frequencies would require a row of towering antennas stretched for miles for appreciable directional effects, but microwaves can be beamed with small light reflectors. For this reason, the trend has been more and more toward microwaves, and within this region towards wavelengths of a few centimeters. Another reason for using rather short waves is that they are less influenced by ground effects that account for the apparent curvature and commercial broadcast waves. This straight line characteristic of the shorter waves is invaluable to obtaining accurate bearing and elevation data. Still, another reason for preferring shorter waves is that for satisfactory reflection, the ratio of wavelength to target dimensions should be small. Detection of planes, for example, requires relatively short waves for optimum reflection. Signal differentiation, pulse modulated microwave radar. Indicators, good old cathode ray tube. Time relations, scanning methods, pulse power and range, pulse power and range. I'm not seeing range, but it's probably there. Position fixing radar. Applications of radar. An immediate application of radar lies in marine navigation. Relatively low power systems with PPI presentation are adequate for both navigation and anti-collision purposes. For airborne functions, however, such systems are not likely to be preferred. For air navigation, precision systems of the position fixing type, like LORAN, offer accuracy, simplicity, and an advantage in size and weight. Ground radar systems, moreover, can simplify traffic control and blind landings. Marine radar. PPI presentation of marine radar permitting blind navigation and furnishing anti-collision protection. Aircraft systems. General applications. Chapter 35, Care and Maintenance of Tubes by C.J. Madsen. Industrial electronic apparatus usually includes circuits and components selected for their inherent stability and durability because the apparatus may be required to operate over long periods without expert attention. Some components and circuits nevertheless require special care in installation and proper maintenance if peak efficiency and uninterrupted operation are to be attained. Extended tube life is often a direct result of such attention. Extending tube life. Following a few general rules usually contributes to longer life and more reliable operation. They are: 1. Use the tube or device within its ratings. 2. Operate tubes at proper cathode voltages as recommended by manufacturers. Measure this voltage regularly with an accurate voltmeter. 3. Apply cathode voltages in the manner specified by the manufacturer. 4. Keep the tube clean, particularly its contact terminals, glass envelope, and anode if it's water-cooled. 5. Maintain an ample supply of cooling medium if it is required. 6. Cathode and anode voltages should not be applied simultaneously except as permitted by manufacturers' ratings. 7. Handle tubes with care. Avoid sudden mechanical or thermal shocks. 8. Store spare tubes carefully. Some tubes require special care as to position during storage. Overload capacity, cathode operation, pure tungsten cathodes, oxide-coated cathodes, thoriated tungsten cathodes, mercury pool cathodes, regulating cathode voltages, tube maintenance, cleanliness, cooling, water-cooled tubes, handling and storage, kinetrons with tungsten cathodes, kinetrons with thoriated tungsten cathodes, plyotrons with tungsten cathodes, plyotrons with thoriated tungsten or oxide-coated cathodes. The tube is operated for 1 minute with normal cathode current only. Normal anode voltage is applied for 5 minutes. Then the tube is returned to the shipping carton or storage cupboard. Tubes of this type may be stored in any position. Spare tubes should be tested every 3 months. All right. Phantotrons and thyrotrons, ignitrons, phototubes, restoration of inoperative tubes, restoring tungsten cathode tubes, restoring thoriated tungsten cathode tubes. References. Chapter 36, Care and Maintenance of Electronic Apparatus by C.J. Madsen. Electronic equipment for industrial service normally is designed to operate for extended periods without attention of skilled personnel. Protective devices and special circuit designs minimize interruptions or serious failures. Some components and circuits require special care in installation and special maintenance, though all electronic equipment requires reasonable care in installation and periodic maintenance if peak efficiency and trouble-free operation are to be obtained. We've got installation, location, power line voltage, cooling media, ground connections, manufacturer's instructions, operation, maintenance, tools and instruments. The following tools and instruments are useful. 1. High resistance voltmeter. 2. Several ranges of DC ammeters or an instrument with several ranges from 10 milliamps to 10 amps. 1-inch paintbrush. Dental mirror, non-magnifying. Lint-free dust cloth. Fine cut file. Burnishing tool. Several sizes of screwdrivers and an offset screwdriver. Set of open end or box wrenches up to a 1/2 inch size or a small adjustable wrench. Special tools as specified by manufacturer of equipment. Basic maintenance operation. Maintenance work can be divided into 5 phases: inspection, cleaning, repair or service, lubrication, and adjustment. All right. Inspection, cleaning, repair or service, lubrication, adjustments. Troubleshooting. All right. And that's it. We're up to the index. Awesome. Well, I'll take you over the farewell cam. We'll wrap up. That's a wrap. I have to say I'm exhausted. I'm going to go off to bed now. I'm sleepy. But we made it through our book. It's a pretty interesting book. A 77-year-old book about electronics, mostly about vacuum tubes. So it's funny that they didn't have semiconductors at all. They did have some things though that I didn't realize they had by that period. Like I've seen that iron bridge. I've seen that mentioned before. And they did have rectifiers, but they were tubes. They weren't silicon diodes. Yeah, it was pretty interesting. So that's the end of this video. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.